Good morning, everybody. Welcome to day 3. I'm glad you can all hear me now. The announcements get shorter as the days progress. Again, we're always thankful for all of our sponsors to help put this event on and make it possible. Presenting sponsor is Millennium Space Systems this year. Gold sponsors are Blue Canyon and Moorhead. Silver sponsor is DHV. And our bronze sponsors are Leaf Space, CubeSpace, and Cambrian Works. Again, they really make it possible for us to use this nice venue and have a number of the nice events that we do. So very appreciative. Make sure you go and check out their booths on all 3 levels. If you haven't seen them all already, now is a great time. The lines aren't quite as long as they were in the first day, so you can get around and talk to everybody in the booths that you haven't hit up already. We don't have any formal activity organized for this evening, but the encouragement, I'll remind you again, when we close at the, around 1:30 today. The encouragement is to attend Farmers Market if you haven't been there. It's a great downtown Farmers Market. It's not just produce, but there's a lot of fresh food and stuff, and it's a great experience if you haven't been there. If you've only been there once or twice, it's fun to go. If you're still here this evening, hope to see you down there. It's my pleasure to introduce our first speaker for the day. Actually, speakers. We have Steve Dunton and Kevin Notberg from Cal Poly. They'll tell us a little bit more about the flying ducks in space. Please welcome Steve and Kevin.
All right, thanks, John. Good morning. So yesterday afternoon, you heard about Cal Poly's collaboration and effort with OWL to fly their duck radios in space, hence the title Ducks in Space. Yesterday, you heard from one of the students on the project, Abby, who talked about our ConOps as well as our environmental test plan and our environmental test facilities that we have at Cal Poly. That was really externally focused. Today, you're going to hear from another one of the key students, graduate student Kevin Notberg. He's going to talk about the internals, the electrical engineering aspect of this project and what we're doing to characterize and improve the performance of the radios. And so I'm going to hand it over to Kevin.
Awesome. Hi, I'm Kevin Notberg, grad student here at Cal Poly. Today, as Dutton mentioned, I'll be talking about the electrical engineering research behind LoRa specifically. In trying to get a duck into space, we're trying to assess whether LoRa as a physical layer signaling is useful and could withstand space. It's been flown before, but we want to teach students and have an opportunity to figure that out for ourselves. So one of the things that happens when you go really fast is Doppler shift, right? And so in orbit, it's imperative that you're going really quickly and moving very fast. And so we have to try and understand, does LoRa hold up to Doppler, right? And we do know that LoRa does have decent immunity to Doppler, but we're trying to characterize it fully in the lab. And so I'm going to be presenting on 2 electrical engineering students' work. John Garib and Ariel Freeman, they're working on this Doppler shift question. So you can see that that's their test setup. And as of now, we've only done static Doppler shift. And we see pretty much negligible effects for static Doppler, 10 to the -7th bit Burr. So that could show up even regardless of your Doppler shift. And so next, and what we're trying to work on in the coming weeks is trying to tool up dynamic Doppler and frequency shifting on the waveform, and hopefully do a full pass simulation on lab. So yeah, that's been one of the research goals. The next one has been looking at, so last year, me and another grad student had worked on bit error rate and truly trying to test LoRa's range capability, right? And we showed that it was really good, 850 kilometers, right? So another group this year is trying to further that effort in 2 ways. One is trying to reach an even better noise isolation and characterize our lab setup even better for attenuated bit error rate testing. And then second part of that is that if we do find issues with the range capability of LoRa, maybe we could jump to another frequency band, right, and use a higher power, right? LoRa is great. Like spread spectrum kind of waveforms are really nice to use for noise sensitivity, power implications, range versus power trade-offs. And so we really do like LoRa, but we operate at 915 megahertz, at least here in the US. And as part of that, and being an ISM band, we are limited by the transmit power that we can use, right? 100 milliwatt DC, right? And so maybe we could jump to amateur, maybe we could go to 2.4 and get up to 5 watt, right? And that would allow us to maybe make a connection farther or for longer, right? In a pass. And so what they're working on is, more Burr testing and that alternate frequency band research. And then part of the Doppler Shift teamwork will bleed into and helping this team as well. So now we're going to take a step up. We've been looking at LoRa PHYs the past 2 years, right? Just the physical layer. How does LoRa work? And so we're taking a step up into, we work with Project Owl, right? And they write a mesh IoT network protocol on top of LoRa. And they call it the cluster duck protocol. I refer to it here as CDP. So we're trying to look at the network layer, at how they package data and send it around on the network, right? That would be defined as your network layer. And so currently what Project Owl uses to define how they operate, when and how they send packets is what we call Aloha, or pure Aloha. The name comes from early radio network research in Hawaii. So, but how pure Aloha works is that when you have data to send, whether it be a user or a sensor device or some comms device, right, in general, you send it. You don't wait and look at the channel. You don't see if there's current activity going on. And so for delay tolerant, low power networks, that actually gets you pretty far, right? When you aren't trying to send a lot of data, there won't be a lot of users on the network constantly trying to send at the same time. But as you have a network that has a lot of activity, has a lot of users, that Aloha scheme will require you to send data a lot, and therefore you'll see a lot of collisions, and your acknowledged network throughput starts to go down a ton, right? And so if you send the data and you don't get it acknowledged back on the network, then you probably have to resend it to make sure it got through, right? And so you really have this big issue where if there's a lot of people, they'll constantly run into each other, and then they'll also try to resend data and run into each other. And yeah, big thing is that your data throughput goes down. And so what I've been looking at specifically is how do we overcome pure Aloha? And it's very simple. It's been done before. It's done on Wi-Fi. It's done on a lot of different communication systems, and it's called Listen Before Talk, or kind of the more official name is Carrier Sense Multiple Access Collision Avoidance, CSMA-CA. So what I did is I implemented a very simple Listen Before Talk algorithm into CDP's network. What it does is it just listens to the network. Is anyone transmitting right before it needs to send data? If so, it will wait and back off and receive that message, and then it will try again. And then if it again is waiting, it'll try again. And it'll do that a couple times, for 7 times in this case, but that's kind of how it works. Listen before talk is just the easy way to think of it. And so how we tested this out was we ran 2 65-minute tests, same time for all the tests we ran. It was a 19-node network. All the nodes had a pre-prescribed amount of, or the rate at which they sent data was preset, and they would send a pseudo kind of random amount of data for every message they sent. And so we ran 2 tests with CDP's Pure Aloha methodology, and then we ran 2 tests with my Listen Before Talk algorithm. So what we saw is about a 70% increase, or closer to 80% increase in data throughput. That was specifically acknowledged data. And what we saw is that over the same amount of time, right, data throughput's data over time, for the same amount of time, we got more data through, and a massive amount more. And so good results on that. And again, if we deploy into space and we have multiple nodes in space, we need to start thinking about collision and avoiding having to resend data, especially when in space you have power density issues. And so if you're constantly trying to resend data, implementing listen before talk is maybe one way to save power. So yeah, I want to say thank you to all the faculty members that have helped us: Steve Dutton, Dennis Derrickson, and Payam Neri. I'm the grad student. Then we have the undergrad, Abby, Cole, and then on the work that I mentioned today specifically came from DE's undergrads: John Garib, Ariel Freeman, Daniel Montgomery, Lucas Lucia, Daniel Zhu, and then also got support from Annabelle Percy. And then big thanks to our sponsor, Brian Naus of Project OWL, and then Marion Green and Yvonne Lynch for supporting kind of the back end side of getting this work moving forward. So yeah, questions? Yes. So yeah, the question was, we're looking at other frequency bands to do comms. Have we looked at the ITU, you said, right? Specification on which frequencies to use. So yeah, that team is currently assessing the different frequency bands that are available to us, both in transmit power capability, and then also in higher level of specification of what are we allowed to use, right? So they're still assessing that, and yeah, I would have to yield to them to get the specifics on what they've found so far.
Yeah, this is evaluation exploratory, and we're looking at the art of the possible. Specifically, have we gotten to a place where we will need a license or gone through the FCC or ITU licensing process? We're not at that stage yet. So this is where we're exploring. And the nice thing about the ISM band is within some constraints, you don't need an explicit license for that. And that's why Laura started there, and we've got good performance out of it, but we're looking to see if there are other things we can do as well. Other questions? All right, one of the other things I wanted to say, we've been really pleased with what we've been able to do with this project, the support we've gotten from OWL, as well as from their sponsors at AFRL, and we're continuing to work this and get external funding. We've got some really good students working this, and as always in academia, they graduate and they go on and they work for you here in industry, and so we're always looking for new people. So if there are Cal Poly students out here who are going to be around in the fall who'd like to continue this effort or some of the new effort, please reach out to us and let us know. We'll be around in the conference if anyone else has a question. I'm here, Kevin's here, Abby's backstage, Dr. Derrickson is sitting here in the front, and we'd be happy to talk with you more about our efforts on this. Okay, thank you.
Thank you, Steve. Thank you, Kevin. Up next is Béranger Virat. He is from Leaf Space.
Good morning, everyone. So today we'll be presenting you a solution that we are currently developing in Leaf Space to improve our ability to support cluster of satellites. Okay. First, I would like to give you a quick introduction on Leaf Space. We're an Italian company, and what we do is a ground segment as a service. So we provide different type of solutions to support either small satellites missions and small constellations. The team is currently counting more than 35 employees our network counts 17 ground stations and is constantly expanding. And for some other numbers, last month we reached the threshold of more than 10,000 successful passes in a month. Okay. So the technological philosophy of this space is to try to simplify as much as possible the access between space and ground. And to do that, we leverage the use of API, cloud interfaces, and also automation. So for example, our customers do not need to book the passes on the ground station. They can just rely on our scheduler. They provide us their mission requirements, and we will automatically orchestrate the use of the network for them. These maps represent our current network and sites that are coming up this year. So in dark blue are the already active sites, and the other color represents the upcoming sites. And I would like also to point out that on some of the dark blue sites, we have more than one ground station. Okay. So now I'll be talking about today's topic, and before starting, I would like to acknowledge the work of my colleagues Lucia Necchi, Vlad Tudor, and Raffaele Bua that have been the main contributor to that project. So to give you some context, last year we started working on a MSPS solution, so multiple satellite per aperture, to support a small cluster. And we demonstrated successfully that this could work. However, we received further requirements for some other missions in which this solution would not apply. The main reason was because the distance between the satellites was too high. And as you can see in this graph here, there is always a zone where MSPA can work. However, if the distance between the satellites gets too big, then we will not be able to support them with MSPA. Another factor that can influence the possibility to support the satellite using MSPA is the baseband support on the ground station. Basically, if the data rate is too high or the symbol rate is too high, the baseband may not be able to work with multiple channels. And so also in that case, MSPA will not be the right solution. So we try to work on another approach to offer that benefits that are similar to MSPA, which means managing to contact all the satellites in one visibility window. So to do that, we implemented this solution that basically consists of taking all the contacts of the satellite, splitting them, and then stitching them together to provide shorter contacts, but at least you get a contact on all the visibility window. The input for that algorithm are the TLEs of all the satellites to be tracked, the minimum duration for each contact, and in order to give some frame to the project, we made some assumption. One of them is we are using only one ground station. The satellites are all operated by the same users to simplify the interface that needs to be exposed. The satellites have the same radio configuration, but we can also reconfigure the frequency during the pass. And each satellite gets only one contact during that full visibility window. So we implemented that algorithm, and the definition of the algorithm is explained in that slide, but basically to simplify all of this, the objective of this algorithm is to provide the longest possible contact and to satisfy the minimum duration for each subcontact. So that's what we've implemented here. The first result we got were a bit funny and a bit disappointing, as you can see here. Basically, it's providing the right amount of contact for the first two satellites. So I think the requirements were 300 seconds. So it was giving 300 seconds for this one and 300 seconds for this one, and then was giving everything else to the third satellite. So we had to implement another rules into the algorithm to force it to evenly spread the extra time to all the satellites. And that's what we got here. I would like also to point out that in this case, we took the original passes with very high separation between the satellites in order to exaggerate a bit and make it more visually visible that we have a good separation. So this is the first proof of concept that we managed to get, and now we are going to work on the next step. Okay. No. Right, okay, sorry. So we are going to look at different paths here, and some nice to have and some other are mandatory. The first one would be to optimize the duration of each subcontact according to the elevation. That would be to take into account the fact that, for example, if you are using a protocol such as DVB-S2, you will have the adaptive encoding modulation, and you will have a lower data rate at low elevation. So in this case, if you want to have the same amount of data in downlink for each satellite, you will need to have a longer pass at low elevation, shorter pass at high elevation, and then again a longer pass for the end of the pass for the long. We also need to create an API to be able to expose all the interfaces to the user and to let them configure those subcontacts. We are also willing to explore the possibility to do a hybrid solution where that would mix the MSPA that we talked originally and this subcontact approach. So basically, when MSPA is available, so in that region, we would operate with it. And as soon as it becomes unavailable, we'd start operating in a multi-contact mode. And the last thing that we need to do, and that's why at the moment we haven't, let's say, used that algorithm on our ground station, is because we need to take into account the moving part of the antennas. And currently, this kind of shape is probably not very compatible with all the mechanics. That would make some acceleration and deceleration that are not that would not please the antenna, let's say. We also think that there are some other use cases for that solution. The first one is winning the TLE lottery. So basically, during the LEOP, or after a launch on a rideshare mission, we could let the user post a list of TLE, and we would track each TLE one by one during one visibility window. In that way, they will be able to establish contact and trying to find which is the best TLE instead of having to wait for another visibility window to do so. Another possible implementation would be to provide, to further deconflict, let's say, the scheduling of passes by using that multi-contact approach for different users instead of one single user. But this solution may be limited to the fact that, first of all, we need to deconflict the scheduling between different users, but also because the radio configuration could be very different, and also the orbits would require us to move the antenna to different points. I will give some concluding remarks on that. So basically, we managed to have a first proof of concept that we would be able to operate this kind of multi-contacts in different operative scenarios. The most important thing now that we need to develop is the API to let the user be able to use that service. And our current plan is to have it online on our network by the end of the year. Thank you very much. If you have any question, I will do my best to answer them. I don't see any question. Right? Okay, great. Thanks a lot.
Thank you to Bérenger Viat. Please welcome J. Arthur Conroy from the University of Florida.
Good morning, everyone. All right, let's see if I can use a clicker. So today I'm going to be discussing ways of optimizing laser communications using evolutionary algorithms and comparing them to more traditional gradient and Hessian-based algorithms. So to understand what the motivation for the research is, it's important to look at the mission we're using. So this ClickBC mission is a follow-on to the ClickA mission you may have seen in previous presentations, where we're going to be using chip-scale atomic clocks to take very precise timing measurements and laser time of flight measurements in order to have precise ranging between two satellites in low Earth orbit, and communicate information across a laser crosslink. We want to achieve full duplex communications with this, that is, full send and receive. And we want to achieve this technology because it offers enhanced size, weight, and power compared to traditional radio communication, and enhanced security. That is, we're not emitting an electromagnetic bubble, we have a more focused beam or cone across which we're going to be transmitting information. It's harder to intercept and doesn't take quite as much energy. So the goals of this mission motivate my work in that the precise ranging and accurate symbol decoding both require precise timing. So our system for measuring the laser time of flight should be both precise and accurate, and this motivates us to optimize the way we measure laser time of flight. So here is a simplified diagram of the receive channel. You'll see a citation on the next page for a colleague of mine's paper with more detail. But the basic idea is that we have light incident upon an avalanche photodiode, which then generates a signal. This signal is amplified and filtered and sent to a time-to-digital converter, which timestamps it. It records the pulse arrival time and sends that pulse arrival time to a decoder, which reads off the symbol and logs the clock offset. This symbol is a means of encoding information that we're going to get into in a second. If you're familiar with pulse position modulation, that's the scheme. So when we have this pulse arrival time, we have first a preamble to run to make sure that the send and receive have a general idea of where their shared time frame is, and then we decode a number from the arrival time of the pulse. We have each of these bins of a given time width, and as you can see here, we have a number which is encoded by the pulse, and the pulse arrival time is not necessarily the same as the intended arrival time. So from this residual between where the pulse actually arrives and where the pulse should have arrived in order to encode this number, we have a residual, an error between the two clocks, the chip-scale atomic clocks on each of the satellites, from which we can obtain information regarding the clock offset. So here is a layout of the decoder. We have our arrival time sent from which we can decode a symbol value, and the leftovers from decoding that symbol value allow us to read the residual. This residual is then passed to a correction function, which prescribes a clock offset for this given pulse based on the residual. This is what we're going to be optimizing in this talk. This clock correction is accumulated over the entire transmission cycle, and we have an accumulated clock offset from this information from which we can accurately decode future symbols. So this correction function is not just as simple as adding the residual to a running tally. In fact, it is not necessarily even linear. So this is an example of a piecewise linear function from which I'm going to start the optimization process. This works considerably better than simply adding a residual, and you can see as you get closer to the center of the bin, the slope, the intensity of clock correction per unit residual is much lower than as you get further away, and is not even the same as when you get even further removed from an accurate pulse. So, in order to integrate the correction function into an FPGA to accomplish all computations within 2 to 8 clock cycles, that is, we don't want a lot of serial computations, we want it to be done in about O of 1 time, and to accurately account for the frequency noise drift between the two chip-scale atomic clocks, and make the lookup table make the correction function amenable to numerical optimization, we store the information for the correction function in a lookup table. We pre-calculate all the values of the correction function for a given set of residuals, and then we have the option to either interpolate or just take the nearest one. But doing this allows us to quickly calculate the correction for an arbitrary correction function to quite reasonable accuracy. We're a little limited by the memory constraints of the system, but it is viable. So this brings us to my point, a little bit of a long walk to get here. But how do we optimize this lookup table? So usually we would do so by defining some performance index, the sum squares of symbol error, and finding the entries in the lookup table which would minimize this performance index. Usually we can do this by calculating the gradient of the performance index with respect to each of the lookup table entries and following that gradient down to a minimum. Maybe even check the extreme values of the entries to see if a extremum might lie there. However, this doesn't work so well when you're using noisy communications. So our chip-scale atomic clocks are good, but they are not perfect. They have frequency noise and they have phase noise. The frequency noise you can think of as variations in the rate at which the two clocks tick relative to one another. And this random variation causes a walk, an accumulation of clock offset between the two satellites communicating. This is not reliable from case to case. Every time you simulate it, since it's randomly generated, this frequency walk can be completely different. Which means that trying to difference on this surface can quickly lose precision. That is, you don't have a reliable performance index on which you're actually taking the derivative. Now, you can try to overcome this by pumping in more cases, simply using more statistical power, but that comes at the expense of computational resources. And at some point, you might want to consider a different solution, in which I posit we can use zeroth order optimization, not referencing the derivative information or not having a difference on this noisy surface, in order to find this solution. So, in broad strokes, we are going to take 3 candidate algorithms representing each of their classes. For the zeroth order algorithm, we are looking at an evolutionary algorithm which takes some of the principles of natural selection and applies them to optimization. So you select the best members of a population of lookup tables, you randomly add a number to a small fraction of the entries in the chosen arrays, and you splice them together, akin to crossover, and then reassess and repeat the process. Getting better in each generation. For our first order algorithm, I chose the conjugate gradient descent algorithm. It's much like a traditional gradient descent algorithm, except that each step that it takes, it ensures is not reducing information from steps it has already taken. It makes sure each step is conjugate to the set of all previous steps. For our second order algorithm, I am looking at the BFGS algorithm and its low memory counterpart, which approximates the Hessian at a given point, calculates the gradient, follows the curvature and gradient information down to the new point, and recalculates. So for the simulation, I wanted to make sure that the variation due to non-algorithm factors was reduced as much as possible. So I took up an entire computer, much to the chagrin of some of my colleagues, in order to ensure that each algorithm had the same amount of computational resources, and all variance is going to be due to differences in times to access memory. I averaged these results over 5 to 15 runs, depending on the algorithm. Some certainly took longer than others. And I averaged the assessment of performance indices at 100,000 cases, but at each step for calculating the gradient or for assessing how well the population of lookup tables was performing, I calculated the performance indices at 10,000 cases. So the lookup tables were kept at a constant number of entries with a constant amount of memory dedicated to each of the entries. And I have the parameters for the phase noise and frequency noise here for the simulated timestamps. I took a stream of generated timestamps and I added in frequency noise and phase noise and passed it to this decoding logic to see how well each of these algorithms would perform. So here are the results. We can see here that the gradient methods, the conjugate gradient, BFGS, and low memory BFGS, aren't getting very good performance. Now, it's a little misleading in that these algorithms perform quite well on their own. The issue is that they're losing precision. They're not able to reliably calculate a gradient. They'll get one iteration, and sometimes not even that, before they simply cannot find a reliable path which they can follow for the next step. Whereas the zeroth order algorithms are better able to develop productive change. You can see here that the extent to which the performance improves is largely independent of the mutation fraction, barring this 5%. But once you have a decent fraction of your entries mutating, it seems that crossover is the better driver of performance improvement. So this brings us to our results for the computation times. So these are histograms for computation times. The evolutionary algorithms, for which there were 10 different mutation fractions, average over 15 runs, are all in their own histogram over here. And the tiger stripe pattern are the aggregated gradient times. So that is all three categories for the C, G, BFGS, and LBFGS. And each of these were averaged over 5 times. You can see that the evolutionary algorithms, in addition to actually being able to make performance improvements, are able to make these performance improvements at an improved rate. And here is the change in performance index divided by the computation time required to attain this change. It follows largely the same pattern as the change in the performance index, largely due to the statistical power of the changes in performance index being averaged over 100,000 cases each. And you can see the ones that were not performing too well, the gradient methods tended not to change very much at all. So dividing 0 by even a large number is still about 0. And I thought, having included the last slide, it should be important to address that as opposed to some other optimization methods, the evolutionary optimization methods are not necessarily linear in their decrease. You can see over a number of generations, we have a very large initial error, which drops rapidly in the beginning and does not adapt reliably from iteration or generation to generation. You can see drop-offs here and here, but it remains largely flat during these interstitial periods. So this speaks to an issue with the evolutionary optimization method in that it is not mathematically guaranteed to find an optimal solution, but it's better than taking several hours to converge, I would argue. So what does this suggest? This suggests that zeroth order optimization outperforms differencing optimization for problems with variable performance index surfaces. So we can apply this if we're optimizing the lookup table, yes, but also if we want to train the weights for a radial basis function for the correction function, we would be better served in optimizing these weights with perhaps a zeroth order method. Or if we wanted to train a long short-term memory neural network for the entirety of the decoder, we would be better served not trying to backpropagate on derivative information and instead address zeroth order methods. All right, I have 2 minutes left. I can take questions if you like. Sir? So we train these on the ground prior to launch. We have, one, the simulations from which this work was obtained, and then we have a test bed that we are constructing in our laboratory at the University of Florida. We are going to develop these on the ground in simulation, and then we're going to verify them on our test bed, and then we can upload these to a satellite that's already in orbit, or we can install them on the machine before it is sent into space. As far as using different lookup tables, largely it's going to be the same lookup table. There is gain scheduling, which is used. Once lock-on is well established at about halfway through the transmission link, the gain is greatly increased in order to make sure we have a lot of control action pushing the clock synchronization close together. And we are looking into having different methods of decoding symbols and correcting the clocks when we have other extraneous phenomena, such as glints from reflections of sunlight, or if we are passing through an intense spot in the atmosphere where there are a lot of charged particles that could perhaps cause the photodiode to send erroneous signals. Sure? So the gradient methods tend to lose precision no matter what you give them. They don't really make appreciable changes, even if you start with, say, random noise. The evolutionary algorithms are able to make changes with random noise, though they do not get as good. They take many more iterations to get towards a solution that is performing well and achieving lock-on if you give them, say, random noise. And you also have an issue where if you start with a solution that is already not very good and you begin evolving it a lot and you don't have a, you're operating on data that essentially doesn't matter, you have not very many pulses coming out into the extreme regions of the bin, and you are simulating that a lot, the evolutionary algorithm will mutate that region so it begins to seem noisy because there's not evolutionary pressure on that. So it's best to identify, if you're going to start with a series of different initial conditions, it's best to identify the region of the lookup table where you're expecting most of your pulses to fall and restraining the evolutionary algorithm to adapting in there where it's actually going to have evolutionary pressure. The gradient algorithm, it's mostly inert to initial conditions as far as I have seen, because it's simply an issue of the performance index itself being unreliable. It can't achieve precision to actually take a gradient step. Over there? Outliers in the data. I don't believe there were any outliers in regards to the gradient algorithms losing precision. I think the closest I got to an outlier was having a gradient optimization algorithm that would that got like 2 iterations in. You can see here I went and, let's see if we can get this go backward. Ah, yeah, cool, it does go backward. I took these intervals to get an idea of the statistical significance of the results. I didn't have to strip any outliers from this data. They were all mostly falling in this pattern. The reason these are bootstrap intervals, it's essentially like a confidence interval that's non-parametric. It is done because this guy over here didn't pass his not Sykes-Picot test, didn't pass his normal distribution of variance test. He was like a p-value of 0.04. So I wanted to make sure it was non-parametric so that all my bases were covered. But the result is basically the same whether or not you're using the t-distribution or non-parametric methods. No outliers were stripped out, and these are the confidence intervals that I obtained. Is that all good? No further questions? All right. That'll be it then.
Thank you, Joseph. Next up is Mont Murad and Neil Bedekar from our own Cal Poly CubeSat lab.
All right. Hello, everyone. My name is Mont. I'm a second-year EE student, and this is Neil.
Yep, I'm a second-year ME student.
All right. So today we're going to be presenting SpriteJet, which is one of our ongoing projects here at the Cal Poly CubeSat laboratory. Sprite is a little microthruster, an RF microthruster that we are building. It's currently in the very early stages of building, so if you don't see many numbers, don't be surprised. Please. There you go. Okay, so the way it works is we are planning to use an RF induced, we're planning to induce plasma using an RF signal at 13.56 megahertz. So the way it works is basically we have, the thruster is going to be part of 2 chambers basically, And we have this chamber right here, which is where the gas will be coming in. And this electrode here will be where the RF energy is going to come from. And basically, the way it works is, if you imagine a tube with a bunch of gas in it, the reason we're using inert gas is because inert gas has a lot of electrons. They're not active, but it has a lot of electrons, which has a higher possibility of inducing a plasma breakdown. And so when we have this inert gas in this chamber with an RF energy going into it, what we induce with this electrode right here is an oscillating electric field. And when we have this oscillating electric field through this inert gas, what happens is eventually the electrons start to break off. And as they break off, we get an ionized gas. And as these electrons break off, they bump into other electrons, which also break off. What's cool about this is that since we have an oscillating electric field, these electrons are going to stay in that spot, or at least move with the gas, but still have some of the remnants of the electrons, which induces even more ionization. Once we have this ionized, it sort of becomes a polar. It's a very, very low conductor. And so we are able to sort of like not necessarily control it using the magnetic field, but more or less direct it into an outward thrust. And it's a pressure differential thruster, and so we won't be actually doing the pushing of the gas, but instead heating it up so that it flows out faster. Oh yeah, sorry. This was phase 1, which was the phase before this one. This was phase 1, which is when this project was initially conceived. It was by Emile Gret, who then came to the Cal Poly PolySat lab to actually build this thruster. The second phase is?
Second phase is James Harper's thesis. So he basically made a lot of changes to the initial thruster that Dr. Emile Gret designed, basically designing an entire CubeSat structure around it. So the main change that he made was changing it to a tunican structure. So the thruster would actually be facing out the plus Z axis of the CubeSat in the tunican itself, and then the rest of the CubeSat would be dedicated to pressure vessel and plumbing, electronics, and all of that stuff. He redesigned the pressure vessel, and by redesign, I mean he designed a pressure vessel, which was validated in FEA for 20.7 megapascals, or approximately 200 atmospheres of internal pressure, to replicate the pressure that would be induced by 500 grams of xenon in the pressure vessel. In theory, this this thruster has a delta V of 20 plus or minus 3 meters per second. And Harper's thesis basically had the following mission plan. Phase 1 would be early communications with the CubeSat to make sure that everything is going well, ensuring that we can actually talk to it. Phase 2 would be actually firing the thruster for 10 minutes. Phase 3 would be communicating with the thruster again to make sure that nothing's blown up. And phase 4 would be end of mission, so the module would deactivate. The mission would have a lifespan of about a week, and the thesis initially used argon as a propellant. However, I'm going to talk about this later, but we want to test different propellants out and figure out which one might be best.
All right, and this is phase 3 of what we have here. Mostly electronics of this project, as the whole project has been kind of conceived. As you can see there, this is our current documented PCB of the whole project. Not really much to go off of, but the plan currently is to actually build it up. But we're hoping to use 13.56, about a 10 watt DC power in, and we're hoping to get 5 watts of RF out of it. We're hoping to make this as cost efficient as possible so that you're not spending an insane amount of money to propel your CubeSat through space. This is our current kind of like high-level electrical diagram. As you can see, only a little bit of interfacing with the CubeSat itself, and there is a reason for that. Is that this is a more kind of in-depth of the whole project. Is that we want to make this project as independent as possible, so that you, the consumer of something like a module like this, would only have to provide power and some communication. So the plan is to have the control module of this project have some ADCS on it, so that what you have to do is send in some formatted commands and not have to deal with the entire ADCS system yourself. So you'd send in a command, hey, I want to XYZ, and then so on. And then we're planning to have, hopefully, modes, so that one, you'd have like a mode where we'd already have a propellant tested for this specific mode, at a certain frequency, a certain voltage, et cetera, et cetera. A second mode where, maybe a different gas, a different propellant, et cetera, et cetera. And the third mode that allows you to control this specifically, to be able to kind of go deep into this and be, okay, I want this to operate at XYZ frequency and at certain amplitudes and so on.
Yeah, so from the mechanical perspective, the James Harper thesis pressure vessel is too complicated to be machined with the resources that we have on campus, which is basically a 3-axis CNC mill. So what we would have to do is essentially 3D metallic print it. We do have one of those on campus, but with the way 3D metallic printers work, we would have to add thermal support structures, which would essentially mean that we have less space inside the pressure vessel to put gas in. So if we wanted to have as much space as possible for this pressure vessel using this manufacturing method, we would have to print it in 2 parts and then weld them together. This has quite a few issues. Well, if we can get it printed without spending too much money, it would be worthwhile to actually try and weld it and test for structural strength. But there isn't really that much flight heritage for welding when it comes to pressure vessels on CubeSats or satellites in general. So for that reason, we're exploring several options, one of which is composite overwrapped pressure vessels. There are a lot of pros to this. Composites are very, very strong, and they would also be a lot more feasible to manufacture with the resources that we have on campus or the funds that we actually have access to. However, this would also mean that we would have to ensure that it's as reliable as possible, basically tracking the manufacturing process from start to finish, because composites are extremely variable in strength. So we would have to make sure that everything is basically the same throughout and everything is super consistent and reliable. Composite pressure vessels also have a lot of failure modes that can't really easily be predicted, such as leak before burst, which is basically the pressure vessel leaking gas before it actually ruptures, or stress rupture, which is basically when the pressure vessel ruptures at a strength lower than its yield strength. And that just like happens over time. It's not really something that you can predict. We also want to do some testing because we have a couple of nozzles designed and manufactured in the CubeSat lab. So we want to essentially replicate a test that was done a few years ago, just so we can get a better understanding of the plumbing, overall power draw, basically how the whole thing works. Because we're picking up this project with essentially little to no knowledge of what has been done on it before. So it would be really great to know like basically what we're working with. We also want to test different propellants and frequencies to kind of tweak it a little bit, figure out what best delta V we can get. The main ones we want to test are argon, xenon, and krypton, among other propellants. And we haven't decided which exact frequencies we want to test, but 13.56 megahertz will definitely be one of them.
Okay, so our current plan as we go conceiving this project into an actual tangible thing, electronically there's actually everything to be done here. Everything from software, making the actual ADCS controls, to actually building the RF system that will be powering the thruster itself. We're planning to have component shape studies hopefully soon, and PCB testing and so on.
Yeah. From a structural standpoint, like I said before, continue exploring different pressure vessel designs, begin designing and iterating upon a composite pressure vessel, and also figuring out thermal insulation for this pressure vessel. Because if we make it out of a material like carbon fiber is pretty susceptible to thermal expansion and contraction, so we would have to include some other vessel or some other material like Kevlar or aerogel to ensure that it doesn't really go through that many thermal cycles while orbiting the Earth. We also need to figure out RF insulation from the thruster module to the rest of the CubeSat that it's going to be attaching to. In terms of testing, like I said before, testing the current thrusters that we have, figuring out which propellant and frequency combination would be the best.
All right. Our sort of entire goal for this project is to eventually make a product for you to use, hopefully for CubeSats. And the main idea behind this project, because something like this has been done before, however, it's not cost efficient. Our idea is to make this as cost efficient for CubeSats as possible, and to make something that we can eventually sell to users eventually. So, yeah.
Cool.
If you have any questions, please feel free to contact us. Top is Neil's email, bottom is mine. Yeah.
If you also have any questions right now, please feel free to ask. Question? I don't exactly know. There was a lot of analysis done on James Harper's end, so it was probably something to do with how long the thrust will actually propel a CubeSat for. Yes. Definitely not anytime in the near future. If I was to give a conservative estimate, I would say probably in 6 or 7 years. Any more questions?
Well, if you have any questions in the future, please feel free to reach out to us if you're interested in the project too.
Yeah, if you're interested in the project, you want to see where it's going, or if you want to work with us, please feel free to contact us. Yeah, thank you so much for listening to us, and we hope you have a great day.
Thank you very much to Mont and Neil. Now please welcome Eran Netheles from Allen Space.
Well, good morning. It's a pleasure for me to be here today. So let's start. Well, let me introduce myself. My name is Aaron Ercellas. I'm a telecommunication engineer from the University of Vigo, and now I'm the electronics area manager in Allen Space. Allen Space, whose core team comes from the University of Vigo, and we're the responsible of the design, build, and operate the first Spanish CubeSat in launch in 2012. We are located in the northwest of Spain, in the beautiful Galicia, a small town near the city of Vigo. Now we employ more than 40 people in the company. We have our own ground station with UHF and S-band capabilities. And our clean room, which nowadays is a little bit busy. We are integrating 4 6U CubeSat right now. We are providers of full missions with our platforms from 1U to 6U, but our other business line is focused on communications. We are experts in communication systems. We come from the university, from the telecommunications engineering school, so we are good with that. And we offer solutions from the ground segment with our ground station kits and mission control software, but also to the space segment with our onboard computer /TTC /onboard software, and mainly our payloads, who are based in software-defined radio. So, for those who don't know about software-defined radio, what is software-defined radio? Well, I'm going to summarize a little bit. It tries to translate all these analog or traditional analog components of a radio system into the digital domain, into software elements, let's say. So the key idea is to put those converters, the analog to digital converters, the digital to analog converters, as close as possible to the antenna. That would be the ideal solution. In the end, we need front ends and analog stuff near the antenna. But that's the key idea, because once you have all your signals in the digital domain, you can do mostly whatever you want, from modulators, demodulators, channelizers, filters, algorithms can be done in the digital domain. And that opens up a huge variety of opportunities. And for those developers who are interested in, there are in the market many different SDRs, from those little dongles, well-known, that you can buy for a couple of bucks, to more expensive radios, obviously with much better performance. So let's go back a little bit in 2015. We were operating a satellite called Serpens, whose mission was to retrieve data from environmental sensors that were deployed all over the world. We have deployed sensors in Spain, Portugal, also in South America, in Brazil, even in Antarctica, which was very nice to set sensor there. And also here in Cal Poly, because by that time, the responsible of the payload of that mission was making his PhD here, so he bring a sensor here to send data from Cal Poly as well. That payload was not an SDR. Its purpose was to retrieve that data, and that's it. But we started to notice some noise, some interference, a strong interference over Europe in the UHF amateur band. So we start with that payload, changing the mission objectives and recording and pass over pass, generating that temperature map. And we could eventually geolocalize the source of interference of that, which ended up being a radar in Eastern Europe. So we said, you know, guys, we are from the telecommunication engineering school, so we can do better. We can make a better payload to accomplish other types of missions and could eventually be in orbit reconfigured. So we base our next payload in software-defined radio. And that is Totem, software-defined radio with a strong flight heritage back in 2018, flying. It's based on the well-known architecture of the Sync 7000 series of Starlinks and the analog devices transceiver that can be tuned from 70 megahertz to 6 gigahertz, and you can do mostly whatever you want. So we have, during that time, developed different applications for this payload, from ADCB receiver, AIS receiver for plane and vessel tracking, but also spectrum monitoring apps, our own IoT communication protocol, but also high data rate communication transmitters, like the one based on DBBS2. And all of these applications can be installed in Totem. Some of them can be run at the same time, some of them not. But yeah, you can do many different things with one single payload. But things have changed a lot. At that time, the most popular probably CubeSat form factor was a 2U CubeSat, 3U CubeSat, but nowadays things have changed. Mission objectives are more ambitious, platforms are getting bigger, and you know, there are companies, now they are not a lot of pathfinders, now there are companies getting revenues and you know, making money. So needs and requirements have changed a lot. So we have also changed our payload to accommodate to these needs. And yeah, I put this meme on purpose. New SDR, let's see, it's a FPGA plus the analog devices receiver. Well, the architecture works, and it's very well supported in the community. So what we put inside is our, you know, our know-how, our expertise during the last years. So this is Trevo, a Galician name, by the way, which is much more modular. We have a motherboard that can monitor and turn on and off the different modules. So the system on chip and the transceiver are in a complete separate PCBs, and this allows us to configure the payload in different ways to accommodate and to provide to accommodate to the user requirements. So basically, the architecture is like this one. We have the system on chip that can be installed in the top left, for example. which contains the system on chip itself, memories, power distribution, housekeeping, and the external interfaces are distributed through the motherboard. So we can have an umbilical connector with JTAG, USB, gigabit Ethernet, but also interfaces that connect to the other modules, like the transceiver, obviously, which in this case is based on the analog devices transceiver AD9361, which contains 2 channels for reception and 2 channels for transmitting simultaneously. So this allows us to generate a truly multi-app payload. And on the bottom side, you can install as well another SoC, another transceiver, becoming in a low form factor payload. 2 payloads, let's say, in the same form factor, truly becoming a really multi-app payload. So for developing applications, there are basically 2 ways to make it. One is by software, probably the easiest way. You can have different levels of abstraction. We provide compatibility with GNU Radio, which is a well-known tool for developing radio applications and radio stuff, with very user-friendly. But you can go deeper and deeper in details within SOAP, SDR, and even accessing the registers of the transceiver itself. But these are software applications that are run in the CPU. But for higher bandwidth requirement applications, you can make use of the FPGA and develop your algorithms in hardware. They are accelerated by hardware. It's a completely different story. So you can have both worlds in the same site. So one of the problems we have seen during the development of this is to evacuate the amount of heat that those guys generate. Especially, I mean, the system on chip, depending on the finite resources of the FPGA you use and the computational load, those little chips can heat up quickly. So we need to get rid of the temperature as soon as possible. And it was difficult engineering stuff to think about this. So the key idea is, okay, we tend to use thermal fillers between the chip and the shieldings, and also there are some straps like that L-shaped metallic structure that connects to the shielding, and that is connected to an external radiator. And those thermal fillers are critical because they provide a soft interface between the roughness of different materials. So it's very, very critical to use these kind of materials. We have tested with Chotherm or indium foil, and that really work. We have tested all the payload right now, making all the testing, environmental campaigns from vibration, EMC, and thermal test. Especially critical, the EMC stuff, because we're dealing with radios, and especially we have radio front ends that tend to be very noisy, especially the transmitter and the power amplifiers. So we need to make sure that it doesn't interfere with other parts of the satellite, especially critical, let's say the TTC or GNSS, that are very noise sensitive. So this is especially critical when testing and when designing this kind of devices. So when it's being used, this payload is already being used in different projects. The one we have with our colleagues at Elliott, which is deploying satellite for 4G and narrowband IoT communications. These are our payload, and the satellite is right now being under commissioning. So I hope we have news very, very soon. But also we are working on a Spanish project called SatMar. It will be a mission of our own, and it's a 6U CubeSat, which will implement in that payload the newest maritime standard communication. Nowadays we have AIS, which is only one direction. It doesn't count with the satellite link. So this new VDS standard will take into account the satellite path, also bidirectional, security, and we are working on that to deploy next year this satellite for these new maritime communications. but also other clients have used Trevo for ADCV, and our feeder link modem is a CCSDS modem in S-band. Well, it will be just to end with. There is a couple of future challenges. I'm not going to be technical here. There is technical stuff to be done with the payload, obviously, but from my experience, these kind of payloads are sometimes a little bit overwhelming for customers, SDR, who are not used. So we need to improve how we give support to our customers and the community. And also, we need to adapt quickly to the customer needs. In this new space era, people try to build a satellite very quick, cheap, fast, but maintaining high quality standards, and that's a bit tricky, especially when this kind of customizations are required. So building a payload as much flexible as possible, it's very critical to accommodate to those deadlines, And also we have in travels, many of you, for example, will be in the same case of shortage, stock problems. So it's also critical. We are trying also to get involved the local suppliers, which are good for us because it's a worldwide sector, but involving also local companies to give the support, it's critical for us. And I think that's all from my side. I'm good time. Yeah. So that's all. Thank you very much. And if you have any question. Well, I know Satellite have talked about this publicly. Okay. So that's why I mentioned that we've been working with Satellite, but I guess I'm not able to tell the exact details. So unfortunately, I cannot answer you that. Yeah, of course. It's a software-defined radio. So different companies have been involved in this project, building this protocol, this standard. So yeah, and as I said in the other slide, we've been using it for our own mission called SATMAR for BDS. It's the same payload, just running different applications, either in software or in the FPGA, of course. Yeah. And you can build around it, many different applications that can be run in the same time. I didn't say that, but the spectrum monitoring app is also be installed in Trevo, in the SATMAR satellite, running spectrum monitoring applications in the UHF and L-band as well, in the same payload. So you can have that flexibility. Well, that will depend on the bandwidth, mostly. If you're dealing with high data rate signals, you may probably want to use the FPGA because, by software, you have a strong CPU, a fast CPU, but you're using software instruction under instruction, and with the FPGA, you can parallelize. You can build. You are building hardware using software, so for these kind of applications, you may want to use the FPGA, and it's strongly recommended, the FPGA. But I know that for quick, this, as I said, in this new space era, that quick, fast, the developments are shorter. So most of our users tend to use the CPU and forgetting about this FPGA. Only the more experts users try to use the FPGA and implement the algorithms in the FPGA, okay? But there is also drawbacks because the FPGA is more powerful, hungry, and it consumes a lot of more power, you know. And but yeah, it depends. Yeah, over there. You said CPUs or GPUs? GPUs. Yeah, I know there are architectures involving the GPUs as well. They are very, very good doing parallel stuff as well. But we are not using them so far. We are focusing in the architecture of the FPGA. We have been working with the Xilinx system on chips so far, and I'm not an expert with the GPUs, but they are being used as well. But it's a different architecture. Sorry. Another one. GPS front ends. You mean the? we use GPS in our satellites, the GNSS, but this is a complete different model. I mean, off-the-shelf product that we buy. No. There are projects. I'm not going to talk about that. But you know, there are many projects, and I think there was a question the other day about what about using LEO satellites for GPS and this kind of stuff. And yeah, there are projects that are thinking of that, and yeah, they try to use the the SDR and FPGA to try to make these algorithms as well. So I guess that's all. Okay, thank you very much.
All right, so thank you, Aron. Now we have a 30-minute break. After 11 p.m., we'll be starting up with thermal and electrical considerations.
Hi, we're going to get started with our first talk after the break. Please welcome Batya Vishnapolske and Adam Sheta from Rebel UNLV.
All right, hi everybody. It's great to be here today. Today we're going to be presenting on doped poly-CO measurements in low Earth orbit, which is essentially the payload of our satellite. Where am I pointing? There. Do you want to? There we go. Okay, so a little bit of background on RebelSat. That's who we're representing. We're a team of undergrad and graduate students at the University of Nevada, Las Vegas, and we're trying to launch Nevada's first CubeSat by summer of 2024. So a little bit about who's presenting today. My name is Batya. I'm studying electrical engineering at UNLV. I'm the deputy project manager, and most recently I just finished an internship at Blue Origin.
My name is Adam. I'm a junior studying computer engineering at UNLV, and I'm the systems engineer over at RebelSat. Okay, taking a little bit of time to talk about what our payload is really centered around. Doped poly-CO is a material that has been developed by Dr. Michael Pravica of the UNLV Physics Department in conjunction with the High Pressure Science and Engineering Center. It is created through the process of irradiating samples of carbon monoxide to create a wide bandgap semiconductor. The experiment that we'll be running on it is a photoluminescent spectroscopy experiment, which I'll hand over to Batya to tell you guys a little bit more about.
So like Adam said, our experiment is photoluminescent spectroscopy. Basically, in layman's terms, you can kind of look at this diagram over here to get an idea of what we're doing, but we will be shining a laser at a sample of doped poly-CO while we're in orbit, and the spectrometer will essentially be measuring the light emitted from the doped poly-CO. The idea is, if the wavelength of light remains constant throughout our entire mission in orbit, then doped poly-CO is proved to be a stable substance. However, if the wavelength starts to change, the nanometer measurement gets a little bit different during orbit, then we know that this is a substance that decays and is not stable in space. So the physics department told us that they want to, for the first 2 weeks of our mission, have a test done every single day. And then once we hit that 2-week mark, we'll only do tests once a week. This is because at first, when we put the doped poly-CO in orbit, we're not quite sure how it'll react. Then after that 2 weeks, we'll sort of get an idea and we'll decrease the amount of tests. So some considerations that we need to think about in order to execute this payload is, first and foremost, power draw. How much power does the laser take when it's actually doing a test? Are we going to be able to do this in eclipse? Second of all, we need to consider data transmission. We obviously need to store results from the experiment and transmit it back to our ground station. And lastly, material survivability during launch. We want to make sure that it survives all the vibrational forces that it will experience, and additionally, we want it to survive throughout detumbling.
Okay, taking some time to think about what doped poly-CO could mean for the future of the industry. It could present a much cheaper alternative to gallium nitride in terms of wide bandgap semiconductors, as well as cheaper than silicon in many areas. Furthermore, because it is a wide bandgap semiconductor, the switching frequency can be made much higher, which allows for complementary capacitors and inductors for circuits to be made much smaller.
So moving on into some of the challenges that we experienced in the development process is, first and foremost, as we know, sometimes it is difficult for CubeSats to get a lot of funding, so we try to maintain a low budget, and we do this by trying to do in-house solutions to many things that we can buy for much more expensive prices. Additionally, if you look over here onto the slide, we have a graph of what one of the spectrometer readings looks like. And as you can see, there are actually 2 spikes. That first initial spike, the larger one, is the light emitted from the laser itself. The second spike, the smaller one, is the light emitted from the sample. So we need to implement a low pass filter in order to eliminate that first spike of light, because we don't care about the light of the laser. We only care about the light of the sample. Additionally, we are testing with Ruby on Earth for now. The reason why is because we know what the output of Ruby should be, which is 690 nanometers. And this way, we can test our spectrometer and the laser and ensure that they don't need any calibration of the sorts. Additionally, we have to put everything into an optical cage in order to ensure that it is able to withstand all of the vibrational forces that happen in launch. And a few things that will be going into the optical cage is the sample itself, the sample holder, laser, spectrometer, and fiber optic cable. So some future steps on how exactly we're going to get this into space. We need to do some further testing once our bandpass filter gets ordered and we're able to eliminate that laser light. And we had a FlatSat peer review done about a month ago, and we had the green light to move on to actually perform FlatSat in the summer. And then after FlatSat is completed, we will be integrating the entire system into our 3U chassis. We will launch, and then we will be able to collect data after we're in orbit. And that's about it. So thank you for having us here at CDW, and I'll take any questions. Yeah, so for thermal testing especially, we want to get a thermal vacuum chamber, and that is actually part of the in-house solution that we're considering, because we could ship it out to other universities that already have these, or we can actually provide people in the organization the opportunity to build that vacuum chamber as well. All right, well, if that's it, thank you so much again. It was a pleasure speaking.
All right. Thank you, Batya and Adam. Now, please welcome Amanda Ewing and Nicole Maggard from Bronco Space.
Tricia. Oh, he's alive. And he's asleep. Ready? All right. Hello, everyone. My name is Amanda Ewing. I am a senior aerospace engineering student in Bronco Space at Cal Poly Pomona.
And I am Nicole Maggard, an electrical and computer engineering student, also at Bronco Space and Cal Poly Pomona. And today we'll be presenting the Proves Electronics.
Hey, so real quick, just a quick agenda. We want to reiterate what our program is, some of the challenges we face as CubeSat designers, a bit of background about the two architectures we are going to discuss, our two designs, Yearling and our future design Chimera, the subsystems of each, and finally the impact we want to have.
So this leads us into the discussion of what Proves is. Proves is the Pleiades Rapid Orbital Verification and Experimental System. It is a mouthful, but we do love our acronyms. And so when we design our boards for the electrical interface, we primarily try to focus on three keywords, which is rapid verification, and experimental. So what we mean by rapid is, you might ask, like, why would you want to be rapid? Primarily, our organization is all college students who are only here for about 4 to 5 years. So we want to be able to learn as much as we can, as fast as we can, right? So, and also as an organizational philosophy, we wanted to be able to design our architectures around being able to, around the satellites being like a lab bench in space for other institutions to implement their own science missions or even payloads.
So some of the challenges we face, to put it bluntly, space is really hard. Everything about the space environment wants to kill us and our spacecraft, making space itself quite the hurdle. Space is also expensive. In cost of parts alone, our first satellite, BroncoSat-1, was about $48,000, just parts. Getting the money to build one spacecraft is hard enough, but building spacecraft and then having a mission failure due to a system outside of our own control is quite the challenge to bounce back from, both monetarily and a little bit emotionally. When rapid design is the goal, standardization is key to a quick and reliable interface, so the lack of standardization is kind of difficult. And lastly, it is relatively difficult to scale up a small CubeSat design to a larger CubeSat, which is something we are very interested in exploring.
So this leads us a little bit into the background of the architectures that our organization primarily focuses on, which involves the PC-104 standard and the backplane architecture. Some examples of the PC-104 style would be like the Pi cubed, as you can see, like the asymmetrical mounting holes, and the Artemis CubeSat kit, which utilizes stacking cards, as you can see. So the main primary difference here is the ability to stack the cards versus slot them into a larger board, which would be like the backplane. So our yearling satellites that we launched on Transporter 6 and Transporter 7 utilize the PC-104 standard, and the Chimera satellite will ultimately be using a backplane architecture. So that leads us a little bit into the discussion about yearling. Both yearling missions were flown on, again, Transporter 6 and Transporter 7. Both use the PC-104 mounting hole pattern, but yearling 1 used the Pi cubed. We primarily wanted to, with yearling 1, to test our communication systems and verify its operation. However, it did not deploy, which was very unfortunate. So we were able to bounce back very quickly and design a brand new architecture that we have dubbed the 3Pi squared. It is a derivative architecture of the Pi cubed. And we were able to successfully attain acquisition of signal, which was very exciting and very relieving that our architecture would work. We were able to develop this satellite for $758 at component cost, which is about 63 times less than the cost of BroncoSat-1.
So the three main design drivers for yearling were cost, speed, and accessibility. To keep the cost down, we designed PCBs in-house and use off-the-shelf components rather than more expensive space-grade components. Although the components we did choose, like the processor and radio, do have flight heritage. This approach also increases accessibility to components, not only by lowering the cost, but also because parts are readily available online with no need for special industry contacts and little to no lead time. Which leads us to the speed aspect. All of our components can be printed and acquired quickly, as mentioned, but we also have internal motivations to design quickly, as we would like our club to be able to fly once a quarter as a long-term goal. On top of these 2 points, we want our satellite to be accessible and open source, meaning the design has to be relatively easy to understand, and we have to offer support to the community that wants to use and build our design. As our colleague Megan had mentioned on Tuesday, we have already begun the process of sharing and supporting our CubeSat community through the Pleiades 5. We accomplished these goals on yearling with a PC-104 style architecture, as mentioned. Our design in particular uses structural mounting brackets rather than standoffs, and a non-standardized connector with cabling running between the boards. This means the boards can function completely independently from one another, with unique pinouts and direct connections rather than being required to operate on a common bus. It also allows for really dense hardware stacking so that we can make the most out of the very small footprint we have to work with.
So this leads us a little bit into our current satellite that we're working on, Chimera, which will utilize a backplane architecture. And primarily, we want to try and maintain similar components that we used on yearling due to flight heritage. So we are also trying to primarily focus in on the scalability of the satellite, being able to make the subsystems as modular as possible and being able to scale them up to as big as whatever the mission would require. So some of the design drivers for this satellite is very similar to Yearling. Primarily, we want to keep everything as affordable as possible, and we want to maintain the open source design for everyone to access. And as said in the previous slide, we want to try and keep this satellite as modular as possible. And so we can mix and match potentially different subsystem cards to fit whatever the needs of the mission and scale it up to as big as whatever we need.
So as mentioned previously, the cards are mounted with brackets and the backplane interface. The backplane has a standardized card spacing. The architecture allows for easier growth into larger form factors, and the wiring is minimal. What I want to emphasize on this slide is the mix and match. Because of the standardized interface, we can use whatever card fits in the form factor. If we need more power budget, we can slot in an extra EPS card. If we want better attitude control, we can make a magnetorquer board. You can even slot in 2 flight computers if you are so inclined. Whatever subsystems adjustments you can fit into the CubeSat, you can do.
So this kind of leads us a little bit into what would be the subsystems that would be included in a Chimera-like satellite. And obviously, you would start with the command and data handling boards, the attitude determination control system, the electrical power system, the solar and flight software, as well as a payload. So first starting off with the command and data handling board, we would like to use in this board are components that we used also on Yearling 1, which would involve the use of the HOPE RF radio module and the RP2040 microcontroller. The RP2040 microcontrollers are actually really inexpensive. You can go online and purchase one for like $1. So they make it very affordable, and we did verify that operation in orbit with Yearling 2. So as you can see, both of the boards have kind of a weird hole pattern, and this is because they are actually on the top cap of our satellite, and so they maintain where the antennas rest. So you can also, what we were thinking with the backplane architecture, being able to slot the system into the backplane as opposed to also keeping it on top. So you could use it for however your mission requires.
The attitude determination control system is a primary example of how we really wanted to emphasize the modularity of the backplane architecture. Although both of our designs have attitude control, the data even suggests that Yearling exhibited detumbling capabilities on orbit, which is very exciting. Yearling's attitude determination was controlled through the main flight computer rather than a separate board. The card intended to be slotted into a backplane would use a Raspberry Pi Zero or a custom compute module to basically think for itself and perform more complex attitude control calculations. 3 motor drivers also live on this board to power a separate attitude control system. That said, this board does set up a very cool low-profile attitude control system that comes default with the kits. And that would be the embedded magnetorquer coils, as you can see in the top picture there. This, when combined with the other coils to be discussed later in the presentation, would offer the ability to slowly detumble our satellite.
So this leads us into the electrical power system card subsystem that would utilize the LT3652 MPPT solar charging circuitry that was utilized on Yearling 2. It would also utilize battery heaters, an inhibit scheme, and burn wire mechanism for the antennas. And so the idea with utilizing the backplane connector is that you would hopefully be able to slot in multiple EPS cards into the backplane and further improve your power budget. So, and one final note on the backplane idea was that we wanted to implement an RP2040 microcontroller on this board as well to be able to allow the subsystem to make intelligent decisions on the power-based decisions for the satellite to turn on and off certain subsystems.
All right, moving on to the power generation of our system. The primary solar components between Yearling 2 and Chimera are almost identical. Both currently use the same cells and external sensors, but the interfacing is very different. Each of the Yearling solar boards are directly wired to the battery board for power, and the I2C sensor data is then bounced to the microcontroller after that. The Yearling solar boards also have motor drivers on the faces, since the embedded coils were the primary attitude control on Yearling, and because there was no designated ADCS card. The Chimera boards operate a bit differently. The XY faces on the Chimera boards directly slot into the negative Z face of the solar system with no extra cabling. A multiplexer on the bottom cap gives the identical sensors on the solar boards unique addresses before sending the data up the backplane. All the data, power, and motor driver signals are then transferred between the solar boards and the backplane via a single connector. As a side note, the coils on Yearling had to be smaller to accommodate the fastener cutouts seen in the top left picture. But the Chimera architecture has an upgraded bigger coil. If you'd like to see any of those upgrades, please come talk to me afterwards. We did not have enough space to include all of the photos, and I'm very excited for that upgrade.
So this leads us a little bit into the discussion of our flight software, which utilizes the CircuitPython, which we have found to be very beginner-friendly. It is maintained by Adafruit. So part of our open source that we have, or will be releasing to the public, will include some of our methods that we have included to easily debug. As you can see on the picture on the right, we have color-coded all of our print statements, so you're able to quickly identify which any given print statement comes from which part of the code.
Now, the payload is the fun part for both designs. Really, you can fly whatever fits. The PC-104 option allows for more customization, but having no standard may make design more difficult for someone new. The backplane would offer stability and standardization, and would encompass most of what a small satellite's payload would need. And it would allow for plug-and-play design, but could possibly limit the design if it requires a specific bus. There's quality of life pros and cons for both, but in either case, the only real limitation is your creativity.
So this leads us into the overall impact of having such architectures available to the public in an open source design, is that with the price point that we were able to obtain with Yearling 2, it is feasible that many institutions, even high schools potentially, could be utilizing this as an educational tool, or even able to use it as a means of sending meaningful science into space and designing cool payloads, right? So.
And I mean, the concrete impacts are huge, but even smaller inspirational moments are incredibly important. The night we launched Yearling 2 was fantastic. It was about 2 a.m. The group of us in this picture up here were all piled into a very small room off of a hotel lobby. We had launched, we had been successfully deployed, and then we had acquisition of signal. Hello, Yearling. And I have never seen such an ecstatic group of people, especially at 2 in the morning. We had received full packets of data. The sense of accomplishment and relief and excitement in the room, we would love nothing more than to share that experience with others with our kit. So, that said, thank you for listening. We will take as many questions as we can here, and if we don't get to you, please email one of us at the emails up here on the screen, or find us before we leave. Find us outside, and we can try to answer some questions individually.
Absolutely.
But yeah, anyone right now?
Any questions? Oh, yes. So the question was, what went wrong with the Yearling 1 deployment, essentially? What went wrong was no fault of our own, unfortunately. Our launch provider had basically lost the ability to deploy our satellite, unfortunately. Heartbreaking. Yes. Yes, so the question was, why use a backplane as opposed to the PC-104 design? And I think actually one of the things that we wanted to really focus on using the backplane architecture was we believed that we could slot backplanes into each other and scale up the design. And so essentially, also it makes it really easy to debug, right? Like if you're able to slot in a card as opposed to having to take apart or deintegrate an entire satellite to access like a stacked card, for instance, right? Oh, yes. So unfortunately, I don't have too much information on how the RP2040 performed, as it was only operational for about 50 minutes, and we're currently trying to still figure out perhaps if it is still alive and we can communicate with it. But we currently were able to see that at least the temperature-wise, right, the microcontroller was able to withstand negative like 10 degrees before we got our last packet, basically. But we didn't notice any performance drop or anything. We got lots of packets in the 50 minutes it was operational. Yes. Yeah. So unfortunately, that was one of the things that we were not able to adequately test beforehand was our thermocouple for our batteries. But we suspect that our batteries, being internal in the satellite, were probably a little bit warmer, probably like -5 at that point. But we did actually do some thermal vacuum testing with Yearling 1, which utilized the same 18650 batteries. And these were able to survive, like, I believe, up to -60 or something, like something pretty crazy. I think that does it for questions. Cool. All right, thank you everyone for listening. It's been my pleasure to talk. So if you have any other questions, you can ask either one of us and we'll be happy to share information.
Thank you so much, guys.
Thank you to Amanda and Nicole. Now, please welcome our speakers from the Cal Poly CubeSat Lab to talk about their project AmDropSat, Mike Cabot and Jacqueline Bond.
Hello, everyone. My name is Mike. I'm a third-year aerospace student here at Cal Poly and co-lead for AmDropSat.
Hello, my name is Jacqueline Bond. I am a third-year mechanical engineering student here at Cal Poly. I am also the other co-lead for AmDropSat.
And we're going to tell you about our project that's going on in lab. It's a very large one that we have going on. So AmDrop stands for, I hope you're a big fan of long acronyms, because it stands for Additively Manufactured Deployable Radiator with Oscillating Heat Pipes. Our project collaborators on this project are Cal State LA and NASA JPL. They're both working on the payload side to develop the radiator, and NASA JPL is working on manufacturing of the radiator, and they are collaborating with thermal testing of that currently. So some background and motivation for this project. High-power CubeSat subsystems are thermally limited currently, so this can include things like high-powered imagers, wideband communications, just electric propulsion, sort of higher-powered applications. And this is really relevant information for exploration of lunar space and that sort of stuff. So innovation definitely exists in the realm of high-power subsystems and thermals. So basically, not a lot of work has been done in the realm of CubeSat deployable radiators. A lot of deployable radiators are limited by, in their thermal performance by the hinge. So the way AmDrop seeks to solve this issue is through the use of an additively manufactured heat pipe, oscillating heat pipe that bridges the evaporator plate and condenser plate. And our mission, AmDropSat, seeks to demonstrate this technology on orbit and raise its technology readiness level to 7 to make it more widespread and available for future use. Oops. So we're going to cover some of the spacecraft design progress now. So as a brief concept of operations of the mission, we first go through the deployment phase. Essentially what this looks like is deployment from a CubeSat dispenser in low Earth orbit, relatively close to what you can think of as the ISS orbit, so around 400 kilometers altitude, 50-ish degrees inclination. It will deploy, begin beaconing. We will check out telemetry and health data with the ground station and deploy the payload, and then initialize our detumbling operations. And once we have tumbled or detumbled to a nominal rate, we can then begin the operational phase. And essentially how it works is the ground station will command the CubeSat to begin the experiment sequence. The mission is designed to be able to handle 50 watts of total heat rejected from the CubeSat through 2 radiators. So 1 radiator at a time will be operated. So this means 25 of heat will be delivered to an internal, to the internal evaporator plate through a heater. It'll last for 30 minutes, and during that 30 minutes, temperature data will be collected through 12 thermocouples per radiator. So that's 24 total. And the data will either be downlinked if it's occurring during a pass or stored for later passes and then downlinked then. And then after each experiment cycle, we will recharge, or just generally, if the experiment's not running, it'll recharge if it reaches a minimum safe level. And then finally, we will reach our decommissioning phase, where the final transmission will be made and the CubeSat will burn up while re-entering the atmosphere. And now Jackie's going to talk a little bit about our structural design.
So here is some structural design highlights we have. Our payload and bus are the 2 main components that make up our structure. Our payload consists of 2 additively manufactured deployable radiators, which have increased heat rejection area to allow for more thermal heat dissipation, as well as our bus is a 3U+ that features solar panels, battery brackets, passive detumbling mechanisms, as well as a 3-board avionics stack. We also plan to use a burn wire mechanism to deploy both of the radiators. Along with our structures and mechanisms, one of the most interesting design features is our battery bracket design. To supply power to AmDrop, we utilize 6 18650 battery cells. The implementation of the 2 radiators on the opposite sides creates a unique set of geometric constraints for the integration of additional hardware. As a result, as you can see, we are limited in volume within that little space down the center of the CubeSat to implement our battery bracket. So here is the early designs of our battery bracket. On the left, if you can see, we have one of the early very modular pieces of our battery bracket. It consists of 7 battery brackets because at the time that was what our power budget determined. We also added holes for raceway and wiring. As you can see, it's comprised of multiple parts, which posed a problem in sense of machining capabilities as well as tolerance stack up. And there was no real structurally efficient way to mount them to the side rails. This posed us to look into different methods. So on the right, we have our tuna can battery bracket design, which allowed us to pack the batteries mostly into the tuna can. Based off of the cells we chose, there was no efficient way to optimally pack the batteries fully into the tuna can, so those protrude into the payload volume. This is our current battery bracket design. It has that inner central battery sheath, which is suspended along the central axis of AmDrop. The battery brackets are sandwiched by 3 main components that run along the entire length of the CubeSat. While, as you can see on the exploded view, we have 4 clips that run in the center of the battery bracket that help connect the sheath together and also provide stability radially as well as double as raceways for the cables. As Mike said earlier, we have 24 thermocouples as well as other connections that need to be made throughout the spacecraft. At the end of the battery sheaths, we have two brackets that allow us to attach the entire battery bracket sheath to the side rails. And they also double for more raceways for wiring.
So I'll talk about some of our testing that we're doing right now. So in addition to all the structural work and systems engineering work that we've done, we also have in-house one of the numerous prototypes that Cal State LA has had manufactured. And what we've been doing with this is performing vibration testing on it. So what this entails is one of our team members, Kayla, machined that interface plate that you can see on top of the shaker table there. This is actually one of our shaker tables in the mechanical engineering vibrations lab. So we use the campus infrastructure to perform this test. And then, yeah, as you can see, there's that interface plate with a lot of different mounting holes because the radiator has to be mounted in a certain configuration, but we wanted to make sure that the plate was adaptable to multiple different types of shaker tables, as well as in multiple orientations. For now, we're just testing it in this orientation, and then on top of the interface plate, you can see that we have the AMDrop itself. It uses these machined brackets that interface with the cylindrical plate there on both the front and back sections of the evaporator plate, which the evaporator plate is the lower part down here. I don't think we mentioned this. And the condenser plate is the outer part that deploys. Yeah, and basically the reason why we're doing this is as an extremely complex structure, we want to make sure that the AMDrop can survive launch loads and that sort of thing. It's a relatively new and untested technology, so we want to ensure that the structure of the additive manufacturing is sound, especially in the spring area here, as that can definitely have some interesting oscillatory behavior. So yeah, we're verifying the response of the payload to launch vibration loads, and as with most vibration testing, this includes sine wave testing and random noise to the various frequency ranges that you can see there.
Here are future plans for AMDropSat. We plan to execute a vibration test on the payload in the stowed configuration within the following weeks. We also plan to do thorough optimization and iteration of our battery bracket design that we showed earlier. This includes 3D printing prototypes to test the wiring and assembly, as well as integration. Testing and integration of the burn wire mechanism through multiple tests. The FlatSat will be made. If you've ever seen our lab tours, we have multiple FlatSat of previous missions that will be made to verify our electric and software systems. We will finally do some finite element analysis as well as tolerancing on our final structures, which will then be CNC manufactured and assembled.
Cool. And that's all we had. So I don't know if we have, looks like we might have time for questions. Additionally, we're also just available around. So if you have something you want to ask us later, we'll be here. Just come find us. We're generally in the main hallway area there. So yeah, thank you. Do you want to do questions or? Okay. If we had any quick questions, we could answer those as well. So the radiator is 3D printed it's additively manufactured aluminum using laser sintering, I believe. This is also, so as the bus developers, we don't go very deep into the manufacturing of the payload itself, but it's a laser sintered aluminum. I don't know what the alloy is, and I'm not sure if they're doing a coating on that. We do use coatings on our CubeSat structures, but I'm not sure what that will look like for the radiator itself. So I don't know if it can indefinitely. Currently, the test plan is to maintain that for the 30-minute test period. Plans may change in the future. I think we're planning on being able to run variable test times. So nominal would be 30 minutes, but it could be more, it could be less. Yeah. Yes.
Our lab develops our avionics stack. If you want to talk about it more, you can feel free to reach out to any of our EEs. It's an integrated board system with a 3-stack, especially through the use of the multiple thermocouples. The 3-stack is very much so necessary for all of our operations. Yes.
Yeah, it's an interesting problem because the payload takes up so much volume, but our board stack that we have in-house is like very small. So we're actually able to accommodate it still within the 3U plus structure. Yes. Okay, cool. All right, thank you.
Thank you.
Thank you to our speaker, Mike and Jacqueline, on their presentation. Now, please welcome our next set of speaker from University of California, Berkeley, Krishna Bhattaram and Nikita Chaudhary.
Hello, everyone. Thank you for joining us today. I will briefly start by introducing ourselves. So we are part of a student organization at UC Berkeley known as Space Technologies of California. And we focus on developing an array of projects intended to probe the frontiers of space technology. So we specifically are part of the CubeSat team. And our mission is to build a miniature satellite in order to contain a quantum gyroscope. So I would like to take a quick moment to introduce ourselves individually. So my name is Nikita. I am currently a third-year undergraduate at UC Berkeley studying physics and computer science.
And I'm Krishna. I am a senior this year undergraduate studying computer science and minoring in physics.
So the premise of CubeSat is to test and characterize a quantum gyroscope based on nitrogen vacancy centers in the conditions of low Earth orbit. So because the gyroscope is based on a low noise quantum sensor, it has a lot of implications on space technology because it has demonstrated to exceed limits of resolution, sensitivity, and driftability limits of conventional microelectromechanical gyroscopes. So our primary objective in our mission is to collect optically detected magnetic resonance data from our payload, which essentially houses our entire experimental setup. So then we can gauge performance and extract various properties and parameters of our device contingent on the environment that it surrounds. Using this data, we can then assess how valid and viable our device is in future space endeavors. So we are currently in the development of our CubeSat, and we have partnered with the Space Sciences Laboratory at UC Berkeley to assist us with the testing and design phases of our process. Yeah, so I mentioned nitrogen vacancy centers as being sort of the basis of our experiment, but what are they? So essentially, nitrogen vacancy centers are defects in diamond, where within the diamond lattice, you have a nitrogen atom occupying a position adjacent to a vacancy. So what makes this structure so special is that it is highly exploitable, and its spin state can be conveniently read out through optical excitation and signal generation. So because it is so sensitive to proximal external magnetic fields and thermal fluctuations, on top of being really sensitive to rotational variations, it behaves as an ideal inertial measurement unit for encapsulating both the roles of a magnetometer and thermal sensor. So in order to implement this, we construct a optical and microwave control apparatus in order to read out rotational data from the fluorescence intensity of the diamond. And by taking advantage of its highly scalable nature, we're able to compact this down to a small form factor to then fit into a miniature satellite and deploy into space where we can evaluate its performance. So just to give a very high-level overview of what the vertical alignment system looks like, we essentially have a laser pointing down to the diamond, delivering optical power. And then we also have a antenna loop delivering microwave power, and it will interface the diamond. So kind of right here, this is the energy level diagram of the nitrogen vacancy. So these green arrows that you see are the laser optically exciting that nitrogen vacancy center from a spin triplet ground state to a spin triplet excited state. And the red arrows are essentially the nitrogen vacancy center emitting a redshifted photon through photoluminescence. And then right next to it here is a nice schematic of the lattice of the diamond. So this red dot here is the nitrogen atom, and then right next to it is its vacancy. And then below it right here is our benchtop setup that we have so far. This is essentially our entire experiment. So right here is the antenna delivering microwave power, and in between here is the laser sandwiched. And this black box is where everything is contained. So this is the diamond. This is how we actually get the physics of our experiment. So that being said,
yeah, so as an overview, I'll be going through the expected measurements we're going to be getting from our payload in orbit. So pictured on the top right, that's kind of the data product that we're looking for from our satellite. And what's pictured is essentially a fluorescence experiment. So we're looking for where are the dips located when we optically excite and probe our system with microwave frequencies. So on the x-axis, you can see the frequency range that we'll be looking through, and the location of those resonances essentially would tell us about both the thermal and magnetic variation in the environment. And so essentially what our payload goal is that we're going to be looking for where those resonances are, and from those resonances, we can deconvolve the effects of both magnetic variation in the environment as well as thermal variation. And then we can quantify the expected sort of noise that we're looking at for the actual deployment of a gyroscope based on like similar principles. So right now, the minimal viable product we're looking for is an ODMR sensor. So we're going to be doing the frequency sweep, like as pictured up here. But we are also looking into more sensitive implementation, which will be based on a Rabi oscillation sequence, as well as looking into coherence times for the multiple nitrogen vacancy centers in the diamond using a Hahn spin echo sequence.
so just a brief mechanical overview of what our satellite looks like. We have a 2-unit form factor. So on the top unit, on the top unit is where we house our entire experiment. So this is where the payload lies. On the bottom unit is where our communication and power systems lie. Our compiled mass budget is estimated to be around 2.2 kilograms. And we expect to offer structural support using an aluminum chassis. And kind of surrounding and encapsulating this chassis will be our solar cells. There's going to be about 16, 4 on each side. We're also enforcing structural support through brass standoffs. So if you saw our benchtops set up in in a couple of slides before this, we used brass standoffs to create sort of the setup of our experiment. And we also are required to have 4 inhibit switches. They're going to be placed on the foot of the base of the satellite. And our antenna deployment system looks sort of like an orthogonal tape measure antenna coming out from the side of the base of the satellite.
Yeah, so with regards to comms and power system, the ethos that we're taking is to be focusing on development of the payload and using largely off-the-shelf components for other things such as comms and power. So for our main controls, including like comms as well as like main computer controls, we'll be using the PyCubed board, which was developed at Stanford with the integrated Hope RF radio for doing downlink and uplink. The PyCube board will be serving as the primary controls, so it'll be the controller and responsible for when to turn on the payload logic, as well as regulating downlink and uplink, and doing other management tasks such as power systems control. So for our power systems, we'll be working with Spectral Lab using 16, as Nikita mentioned, 16 solar cells, and they'll be interfacing directly to the PyCube board and the power logic on the PyCube board. And through that logic, the PyCube will be connected to the battery board, and essentially the power systems management will also run through the PyCube. And this is kind of a brief overview. It's a schematic that we have of our power systems. So essentially, the PyCube board lies at the center in terms of both logic and power. And it will deal with the communications with the payload, which has its own microcontroller for the sakes of having more high precision timing to run experiments such as the Rabi oscillations and Hahn-Spinnaker experiments. And through there, we interface with all of our microwave boards, our laser power generation boards through the payload microcontroller. And downlinks will be done through the comm system, which is integrated on the PyCube.
All right, thank you so much. If you guys have any questions, we'd be happy to answer them. Yes.
Yeah, so this device is much higher power. So it does have the active query of the system. So you use the laser, you use a microwave to conduct fluorescence sweeps. But the primary objective was to have a system that would be much lower noise, could be used over long duration space missions. So over time, MEMSs accumulate error due to drift, which this payload won't accumulate.
Any other questions or? Yes. Yeah.
Yeah. Yeah, so one of the main selling points about this gyroscope technology is that the quantum physics of the system is pretty well understood, and it's also pretty simple in that it's a two or three level spin state system. So the effects of thermal excitation and the effects of environmental variation, such as due to a magnetic field, are theoretically pretty well understood. And we're working with two researchers on campus who actually developed the gyroscope technology. So they have run it through testing for variation in terms of temperature and magnetic field. And they found that they're able to pretty deterministically deconvolve the effects of environmental variation.
I think the exact rate is something to the magnitude of 4 orders of improvement. But yeah, essentially we want to take this gyroscope and see how it performs in space in the conditions of LEO. So then we could see, okay, is this something that is applicable for other space endeavors and applications? All right, if there's no other questions, I'd like to thank you guys. Okay, thank you guys so much for listening. Thank you to our last presenters. Now please welcome Hannah Gulick from the University of California, Berkeley.
Hi, yes, so my name is Hannah Gulick. I'm a third-year graduate student at the University of California, Berkeley, doing my PhD in astrophysics. Oh, thank you. And today I'm going to be talking about how we can kind of put all of these technologies that we've been talking about all week together into something that we can do some pretty amazing astrophysics. And that is CURIOUS, which stands for CubeSats for Rapid Infrared and Optical Surveys. CURIOUS is a concept for a constellation of CubeSats that's being led by the University of California, Berkeley, along with Space Sciences Laboratory. Our PI is Professor Jessica Liu, and we're partnering also with Livermore National Laboratory. Okay, so I'm going to dive right into the science that kind of justifies a mission like Curious. Currently, there are many open questions having to do with compact objects, such as neutron stars and black holes. We define this here as the death and afterlife of stars. We're really interested in this transition from stellar lifetime into what they do afterwards. These questions pertain to things like the basic properties, such as what are the different masses of black holes? How many black holes of different masses do we have? Is there a difference between the most high mass neutron star in the universe and the lowest mass black hole? Additionally, we don't know a lot about their origins. So if you've ever taken an astronomy class, you were probably taught that your small stars up in the top, nope, down at the bottom, go through their life, and then they kind of burn up, maybe balloon out a little bit afterwards, and essentially shed their outer layers to leave behind a white dwarf. Your more medium-sized stars will maybe explode, maybe not, and create a neutron star, and then your most high-mass stars are going to be the ones that inevitably create these black holes. However, we don't actually know the boundaries in between the masses of these star sizes and what kind of compact objects they're going to create. It depends on things like stellar metallicity and other properties as well. Additionally, we don't even know things as basic as their populations. We have estimates for how many black holes we think there are in the Milky Way, but we have very, very few observations. And finally, if we don't know anything about their origin or populations, we also don't know much about their evolutions. So again, if you've ever taken an astronomy course, you can imagine I just opened up a huge regime of science, anything to do with compact objects. This plot here is showing you an example of some of the transient science that we can do that related to compact objects. On the x-axis is just the duration, so from seconds to days to years, how long these transient events last. The y-axis doesn't have any meaning. On this plot, Curious will be able to detect all of these different transient objects. However, we have based our first model of Curious off of a specific science case, and that is black hole microlensing, which I'll describe a little bit more in a minute. But essentially, through black hole microlensing, we can detect isolated stellar mass black holes, which there's no other way to currently detect those in the Milky Way or the universe. And I'll note here that only one isolated stellar mass black hole has been detected so far, and we expect something like 10 to the 8 of them in the Milky Way galaxy alone. So returning to gravitational microlensing, just a quick crash course on this. It's a really cool phenomenon where you have a background star on the sky, and then you have some kind of object, like a black hole, which passes in front of your background star. So that's what this top animation is showing. The yellow star in the middle is your the background star. The red source is our lens, so a black hole passing in front of it. And when this happens, two things occur. First is the image of the star is disrupted, and it's split into two separate images. These are those two blue dots that are moving above and below the event. The second thing is shown on the bottom panel, and that is the gravitational mass from the black hole in front of the star is going to cause more light from the star to bend and focus into our telescope. So this turns into an amplification in our telescope, which you can see on the bottom. And so if we just measure the brightness of the event as a function of time, we're going to see it get brighter, and then it's going to get dimmer afterwards. And this is what we can actually measure with our telescopes. Now I'm showing you a comparison of Curious's expected light curve with OGLE, which is one of the best microlensing telescopes currently. And there's two main things you want to take away here. And I'll show our challenges here as well. So Curious is the darker color. One is the error associated with Curious's light curve is much, much smaller, so we are able to better constrain these peaks. Second is that we're able to cover more of this time baseline. So time is on the x-axis. OGLE has bigger gaps than Curious, and it's really important that we fill these in so that, again, we're able to constrain this peak. And there are some big challenges that come with microlensing, and this is why we aren't able to constrain it well right now with our current telescopes. And it's really based around the fact that microlensing is a transient phenomena that occurs anywhere from 1 to 1,000 days in time scale. This means that you cannot just look up at the sky and hope to detect a microlensing event. You have to repeatedly sample the same part of the sky over and over and over. Additionally, it's not a super strong event, so you need something in space in order to achieve the error necessary to detect these events. And so CubeSats actually allow us to do this. And our solution to this is Curious. We want to employ 316U CubeSats to do all sky, all the time observations. We'll be able to detect these microlensing events as well as all of those other science cases that have to do with supernovae, merging neutron stars, merging black holes, amongst many other things. So this is kind of the idea for our Curious bus structure. It's a 16U bus, and we're going to have a telescope inside of it, which is shown as this blue chunk in the middle. We're going to have a 15-centimeter aperture for our telescope and look in the optical bandpass from 0.45 microns up to 0.9 microns. Our nominal duration for the lifetime of the mission, once all of the CubeSats are in space, is 5 years. This should be plenty of time to accomplish the science we need, and provide all of our data to the community. For astro people, our sensitivity is going to be down to R equals 21.7 magnitudes. This is really good for a CubeSat. It competes with some of the best telescopes in space right now. Of course, James Webb and TESS are able to do much better, but they have much better telescopes as well. Our cadence, we're going to do 30-second integration times and stack these into 15-minute total exposure times. And we'll have 90-minute gaps that are due to the orbit, and then 10 months gaps over the year. This just has to do with the sun being in the way. We can't look directly at the sun, so we lose some targets for part of the year. And then orbit, we're going to go into an LEO sun sync. The heart of our instrument is going to be this monolithic optic. This is a really novel and cool way that we are employing a telescope on a CubeSat. So we all know CubeSats are small. There's not a lot of room to design a really high-power telescope. However, by using a monolithic optic, which is a solid piece of glass in which we carve our telescope into, we're able to get a very small form factor on our telescope and very good, it meets our requirements very, very well. And so up in the left-hand corner, I'm showing you the monolithic optic. It's composed of a transmissive doublet on the left side, followed by the main optic. And then on the back of the main optic is painted a reflective coating, which acts as our primary mirror. And then on the inside, the light bounces back up from our primary mirror, and there's another reflective coating painted on our secondary mirror, and then it goes into our detector. Some of the specifications for this optic, we're looking at a field of view of 6.9 degrees by 4.9 degrees, which is very large. And another thing that's really driving our instrument is resolution. So detect microlensing, you have the best chances if you look in really crowded spaces where there are a lot of objects that can be microlensed. But when you're doing this, there's a lot of other variability that's also going on at the same time. So we need really good resolution for our telescope to separate out our sources from other sources of variability that are going on. And essentially, we're just getting a 1.5 arc-second resolution in the center, which is perfect for what we're trying to do. And just to highlight here how big our field of view is, the yellow box here is the Curious field of view, and then it's kind of hard to see, but up in the left-hand corner, the tiny, tiny yellow box is the Hubble field of view. So we're able to take the entire LMC in a single field of view, which is really important because when you're thinking about designing a constellation, we want as few CubeSats as possible for monetary reasons, but also for sustainability of space. And so having a bigger field of view, we need less CubeSats to cover the entire sky. So there are a couple challenges that we've run into, one of them being our pointing instability, so using our ADCS system. So for pointing for a CubeSat, it's our ability to point at a star in the sky and stay fixed on it without it jittering across the field and getting into a bunch of different pixels. This lowers our resolution, and we need very good resolution, as I mentioned, to do our microlensing science case. So Curious is going to require that we have less than 1 arc-second of jitter over a 30-second exposure, which is much better than anything that's currently been put into space. Previous missions, such as Asteria, have gotten down to 1.6 arc-seconds, and we're trying to push this boundary even more. So this data here is showing some of the lab tests that Dr. Steve Beckwith has been working on in our lab. He's finding so far that we can get down by using also images from our science payload, as well as the star trackers to improve our errors. We can get down to a 0.3 arc-second RMS jitter. I will say take this with a grain of salt. This is all being done in the lab right now. We do have some reaction wheels that we're working with, but this is not space qualified. It has not been shown. This is very much still an active area of research for us, and we're working with a lot of different companies to see if we're able to achieve our requirements. The second one is going to be data downloading. As you can imagine, putting a survey into space, you're going to have a lot of data. Even with data compression, we expect something like 1 gigabit per second for 300 satellites. This is going to be expensive. We're going to need a lot of ground stations positioned across the Earth. This is still very much an open problem for us. We're working with a set of companies as well, trying to figure out how we can manage all of this data. Okay, and then before ending, I want to return kind of to our science case, since I am an astronomer by trade. And here I'm showing you the 2 important parameters from microlensing. On the x-axis is the duration of the microlensing event, so how many days it is. And then on the y-axis is something we call the microlensing parallax. And essentially what we get from the microlensing parallax is the mass of our object. And if you plot these two against one another, you can see that we have our population of stars, white dwarfs, neutron stars, and black holes all marked. And what happens is the black holes separate themselves from the rest of the population. And this is really important because if you're just looking at a light curve, you can't tell what compact object you're looking at. But if you can then plot its pi e and TE, you can say, oh, this is in fact a black hole. So we simulated some events, which is shown on the left up there. And then we used a Fisher matrix analysis to add error bars to these events, which is what's shown on the right. And you can see with Curious and the requirements that we've built for this, this constellation, we're very much able to separate out these black holes. I'll compare it now to OGLE, which is the ground-based survey I was showing before that we use for microlensing currently, and you can see that there's no separation of events here. So we're performing much better than the best telescope for microlensing right now. And the takeaway from this, if you remember I mentioned at the beginning, we've detected 1 stellar mass black hole so far. We'll detect 50 black holes per year per a single Curious field of view in the galactic center region. So we're already doing much, much better, and this is just with 3 CubeSats. With the full 300, we'll detect more than this per year. And then I guess the big question is why now? So private industry has really been pushing the envelope of technology with constellations. Academia has a little bit of catching up to do, but there's a lot of science that can be done with constellations. So we're kind of interested in exploring this space while also doing our science. Additionally, early constellations have really shown the need for mitigation techniques, thinking about sustainability in the future of space and the human right to dark skies. So before ending, I do just want to comment on that a little bit. While Curious is doing some very cool science and also doing some very cool tech demos, it is a big hope of ours, or intention of ours, to pave a path to safely launch constellations into space with sustainability in mind, with the future of space in mind. So 2 of the major concerns, one big one for astronomers is visibility, so ground-based telescopes can detect satellites like Starlink quite easily. The other one is overcrowding. We're all concerned about collisions in LEO. So as opposed to like Starlink thinking retroactively about some of these problems, Curious is very much trying to design this into our concept. And we're thinking about how we can use baffling to lower the light that we're reflecting back down towards Earth. We'll also think about orbit design, which ones are going to be the least likely to provide collisions for us, and also which ones are going to be the least likely to reflect light down to Earth. And then we'll also incorporate propulsion on all of our CubeSats for anti-collision movements. And there's some intrinsic things in the Curious design as well that automatically set it up to be sustainable in these senses. One is that our 16U CubeSats is a factor of 100 smaller than any Starlink satellite, so it's going to reflect a lot less light. Additionally, it's harder to collide with something that is a bit smaller, though that is definitely still a concern. In addition, one final thing is that the gentleman's agreement, we will leave space as soon as we are done with it and return it for the use for other projects. And with that, I would like to take any questions and would be interested in talking to anyone who has some ideas for the future of Curious. Thank you. Yeah. Yeah, so altitude, we're looking at 550 kilometers, maybe a little bit higher if we can get up there. It's kind of, there's a lot of CubeSats, so it's going to depend on what launches we can get. And the total mass for them, I think they're around 25 kilograms, but I would have to double check on that for you. Mm-hmm. Yeah, so we've been talking to some companies, so we're kind of doing this in steps. We proposed for the first 3 CubeSats so far, which is much more manageable to work with than 300. And so what Curious is doing is kind of developing with a lot of companies. So we're going to put kind of our eggs in a basket for the first 3. We've been talking to Leaf Space, for instance, so far, and see how it works with those 3, and then maybe develop along with that company. If another company goes further by the time we get 300 up there, then we'd likely go with that one. So there has been some conversation going on there, but I would say data downlinking is still very much a challenge for us. Yeah. Yes, so we have some reaction wheels in-house right now just to do our own experiments. We will not be developing the ADCS system for these satellites. So far, we've been talking with CubeSpace. We've also talked with StarSpec. We have a few companies that we've been discussing with. Nobody has achieved the pointing that we need so far, so a lot of it is theoretical at this point, though there are some CubeSats in space right now, or will be soon in space, that will do the tech demos for us. Propulsion will also just buy from off the shelf or through a bus contract, essentially. Yeah. Yes, absolutely. So first question, rapid response. We do have an idea for target of opportunity. We will not have satellite-to-satellite communication going on, so our response time will be a little bit delayed. It will be held to when we're able to downlink. We're expecting to downlink, I think, 3 times per day per satellite. So that's kind of the response time that we're looking at. However, some of the optical afterglows are long enough for us to still target them with our satellites once we get the information. Roman and Rubin. So Roman is a great counterpart, or I guess Curious is a great counterpart to Roman. Roman, for anyone who doesn't know, is a big microlensing survey conducted by NASA. It's going to be a very large telescope going up into space around 2025, I believe. And they're going to have big gaps in their data. They're only going to look at a certain patch of the sky for, I think it's like 70 days now, 2 months-ish. And then Curious will fill in the gaps in between these patches. So that will be fantastic. Additionally, Roman is going to be out at L3, I believe, or L5, one of the Lagrangian points. So we'll be able to do instantaneous parallax with Curious, which is super important because we can then determine the distance to our sources, which then reveals their mass and a lot of other characteristics. Rubin performs much better depth-wise, but again, it's constrained to the ground. So they can't see the entire sky, and they can't do the sampling that we are capable of doing with Curious. Yeah, good question. Yeah. Yes, yeah, it'll get half the sky, but it achieves a much better sensitivity than Curious is able to do. But again, we have 15-minute cadence, which is really our big advantage with Curious. Yeah. Just to make sure I heard you right, kind of explain how we're going to run our pointing system? Okay. I will explain it as well as I know. I haven't been working actively on the pointing system. But so what we're thinking of doing, the typical system is you have reaction wheels and then you have star trackers. And your star trackers are looking out their little telescopes and they kind of identify a bright source on the sky and they're like, oh, we know what this star is. So we're kind of locked on to, we know where we are looking at and we're going to lock onto that. And the star trackers continuously take data at some sampling rate, preferably a very high sampling rate, and then send this information into the reaction wheels, which then point your spacecraft to keep it fixed on that star. What the problem we're running into is that the error associated with the data from the star trackers is too high for the reaction wheels. So the reaction wheels are able to perform to the standard that we need them to. It's just the errors associated with the data being sent to them isn't high, or aren't good enough. So by sending the payload data in where we have a very good telescope and are able to have very fine precision on our sources, or fine looking at our sources, we can reduce these errors and therefore the reaction wheels will behave better. And so in our payload camera, we're intending to have little regions of interest that are like 16 by 16 pixels and have a very bright star in each of these regions, maybe like 3 across the field, and then send this data into our reaction wheels. Yeah. Yeah, so if you do the math with our current field of view in the 300, we will not cover the entire sky. It kind of comes down to money, and it kind of comes down to thinking about not putting too many satellites into space. So what's nice about the constellation concept is that we have economies of scale, but also we can do different integrations of the satellites, so we can develop them further as the constellation goes on. So these first CubeSats are developed specifically for this microlensing science case. Future ones could have bigger field of views. So we're kind of thinking with 300, we can get greater than 50% of the sky. That's our baseline requirement right now. And maybe even more than that if we change the field of view in future iterations. Awesome. Thank you so much, and feel free to reach out if you have any other questions.
All right, so one of the challenges that we've noticed over the years with CubeSats, at least a little more recently, I think has to do with perhaps some of the origins of just see what you can get on orbit and get it to fly, right? That was the first couple years of CubeSat development. Can we make this work? And people tended to ignore a lot of the different design factors, right? So for instance, people tended to not really care about thermal analysis or thermal design in their spacecraft. And they were largely able to get away with it because the LEO environment that the first CubeSats were launched in was relatively benign, right? Compared to some of the other environments that our CubeSats are being launched in or being proposed for now. And as a result, I think some people have just sort of forgotten or didn't realize they should actually do a thermal analysis or at least understand some of the fundamentals of thermal analyses for your spacecraft in order to correctly answer the question, right? So when CSLI comes back to you and says, golly, we need to change our orbit, we had you in an orbit of 380 kilometers and we want to boost you to an orbit of 450 or 480 kilometers because the launch changed, is that okay? Right? A lot of people are like, oh yeah, I like a higher orbit, it's going to last longer, right? But they don't actually go back and consider potential thermal impacts of that orbit change. Because again, we're not, from a CubeSat community, we're not nearly as accustomed to that as the larger spacecraft are. Likewise, as we're trying to send more of our CubeSats to the moon and interplanetary, thermal becomes a much bigger consideration there. So if our mindset has been a traditional, golly, we're in a LEO orbit, and we're not going to really pay attention to thermal, and now we're going to propose lunar missions, it is sort of a big shift in our mindset. As a result of sort of that trend and the idea that we want to pack more and more capability into the CubeSat, right? The denser we make the CubeSat, the larger solar panels we put on the CubeSat or solar arrays, it's going to take, we have to be more aware of our thermal management. Anyway, so that's sort of the impetus for our next and our final panel here. We have a panel of folks who are expert in thermal analysis. Hopefully you'll get some good value about the discussion that happens from the panelists. So could the panelists please come on out? They're there somewhere, I promise. All right. So we have 4 panelists here in person, and we have a couple on Zoom. And so they'll go through and introduce themselves, and then they have some discussion, and then they'll take some questions. So please welcome our thermal panel.
Welcome to thermal panel. Actually, I didn't expect to see so many people. I thought that mostly people will be here and much less here. So thank you, really. We understand that we are the last event in a very good conference. And so then welcome to thermal. And I see that really thermal problems do bother people. And so we are going to talk today about this. So let's do first a very short introduction. This is Boris Yendler. I am very really concerned with thermal issues. And this is one of the reasons why we have this panel. So then another, Chris, can you?
From Aerospace Corporation.
And can you give you a couple of words about yourself?
Yeah, so I've been working in the thermal industry for about 6 years now. I started at JPL in 2016, working in the thermal division there. I worked on the thermal subsystem for NASA's big flagship mission, Europa Clipper, which is currently being assembled over in Pasadena. I also worked on Euclid spacecraft, which is kind of like the European version of James Webb, and a few other little missions here and there. And then I've been at the Aerospace Corporation since 2021.
Yes, hi, I'm El Wittigassid. I'm the Deputy Program Manager for NASA's Small Spacecraft Technology Program. I've been involved in the development and utilization of CubeSat since NASA's first GeneSat mission back in 2006, and you know, it's kind of evolved along the way. Just recently finished the program management, or actually continuing on the Capstone mission, which is now in the near rectilinear halo orbit.
Okay, thank you. Dr. Thomas?
I'm Tom Svitek. I am from the local company doing small spacecraft technologies here in San Luis Obispo. We pretty much focus on propulsion and high-end power systems. So basically thermal is very key, keeping it not too hot, not too cold on both ends. I'm actually not a thermal guy. I'm a systems engineer. So we kind of view as a users of the thermal engineering, you know, so I have a maybe different perspective.
The format is such, we're just going to talk about our favorite topics, about 5 minutes each, and then we will have pause for your questions. Now, if you want to send questions, just please to write down, and or this after first round, you raise hand and just ask
Boris,
questions.
I think there are people online, right? There are other panelists online.
Oh, I thought they are. Oh, yeah, you're right. Okay, sorry, John. Please introduce yourself. We can hear you.
Hello.
Okay.
Now you.
Actually, it's a very strong echo. Maybe we need to mute ourselves.
He has to mute his mic.
Hello.
Yeah, they got an echo.
Can you mute the audio on that computer? Yep, I think I am. Looks like it's not muted. Did I just come off mute?
Sorry, we have some glitches.
Where's the mute button? It should have been that. It's good.
John, can you try one more time?
Hello. That sounds better.
Okay, now we need to have louder. Huh? Yeah.
Should I speak more loudly?
Okay, John, you're on.
Okay. So I'm John Thayer. I work with the Boyd Corporation, which was previously known as Avid, and before that, Thermocore. I made a lot of heat pipes in the last 25 years, and approximately the last 15 years, I've been supporting a number of space applications. Most significantly is a NASA loop heat pipe for the PACE orbiter, which will be observing ocean colors. That will be launched in approximately 1 year. And in addition to quite a number of commercial space customers.
Thank you, John. So, Mackenzie, you're on.
Hi there. Can you guys hear me okay?
Yes.
Yes. Oh, great. Okay. Hi, my name is Mackenzie. I currently work for Advanced Cooling Technologies, ACT, which is also a heat pipe manufacturer. I'm relatively new to the world of heat pipes, however. I'm mostly a spacecraft thermal analyst. And my bona fides there, I spent about 5 years at SpaceX working on Starlink as the thermal analyst there. So, looking forward to the panel.
Thank you, Mackenzie. So now we're going to panel. So the first is Elwood is going to talk. Please.
Yeah,
to say something, couple
yes,
words.
Boris asked me to. It's been a long week. Boris had asked me to more or less talk about some future NASA missions or missions in planning that would most likely have high power requirements. I think one of the things, rather than just talk about any particular one mission, is kind of highlight the fact that, you know, over the years, a lot of the small sats and CubeSats have evolved, and you know, from the small low-powered beacon radios that just needed a half-watt of power to basically what's available now, because as the NASA missions increase in their complexity, the utilization of all the different comm systems, power systems, as well as propulsion systems have really required a significant increase in the power requirements for the spacecraft and the overall mission. When we flew, for example, GeneSat, we had a micro-hard radio, put out about 1 watt maybe, but it required something on the order of 2 to 5 watts of input power to get the 1 watt out. Now we're flying the Capstone mission that basically required 3.8 watts of power by using the Iris radio. It was also coupled with a TUI S-band radio for doing crosslink experiment with LRO. So there's another 2 watts. We flew Tomas's hydrazine propulsion system that required about 15 watts?
Yeah.
About 15 watts, and then there's other camera sensors, and then there's the processing power. The average power of the Capstone spacecraft, the requirement was somewhere around 182 or almost 200 watt hours of power to run that mission for 6 months. And so you can see that, you know, when the first 3U spacecraft that we flew generated somewhere around 8 watts of power, and then now you're up to, you know, 182, you know, watts of power for a single spacecraft. As you start to go into some of these other missions, like the Dragonfly mission, the helicopter that will go to Titan, they have a nuclear thermal power system that's recharging this huge battery pack. So as far as power requirements are, it's going to be driven by the mission. And one of the things that Boris was trying to get me to define is what is the maximum power, and it's actually going to be defined by the mission requirements. If you look at some of the Hall thrusters, for example, some of those EP systems run from 100 watts to 600 watts. The Hall thrusters can get up to 20,000 watts. So, you know, you're looking at all these different elements of your space mission as you look at different comms, like Cesium Astro will put a radio tower that'll give you 4 comm systems so that you can do TT&C as well as your other command control and other communications as well as your sensors. So as the complexity of your mission goes up, the use of different sensors, whether they're LiDAR or other optical sensors, hyperspectral imagers, they're going to define how much power. And you can only just see that when you're trying to operate a lot of these systems and you're trying not to just duty cycle them, but use them in parallel, your power requirements go up significantly. A lot of the spacecraft buses that are coming on board now are starting to get up to 300 watts of orbit average power available to the payload. So now you're just seeing for these missions, especially as you go into deep space exploration, the power requirements are going to go up just because you have a lot of navigation instrumentation that's going on, being utilized.
Thank you, thank you very much for review. This, as we see right now, the power of spacecraft, goes up, and so now the Chris would like to tell us something about thermal management.
Yeah, so this little section here is kind of motivated by some of my experiences working in thermal control in the space industry. I'm sure, certainly myself and I'm sure everybody else on this panel has seen situations where people have had sort of misconceptions about the way that thermal works in space. And so this is kind of my attempt at trying to distill 5 years, 6 years worth of experience, perhaps more for a lot of these guys, down into 5 or 10 minutes. It's not going to be the best. I'm trying to keep it kind of high level, but hopefully give you enough of a flavor so you can understand some of the challenges that we face when it comes to thermal. So really, at the end of the day, let's start with kind of the basics of Thermal 101, right? So really, the thermal system on a spacecraft, regardless of how big or small your spacecraft is, it really just has one job, right? And that's maintain the temperature of everything on board within some acceptable range. Usually those ranges vary based on the particular component involved. Fun fact, Goldilocks was actually a thermal engineer. So, basically we want to make sure that things don't get too hot or too cold, but they actually stay just right. So that part got left out from the story, but she was very much a thermal engineer at heart. And so you might think, like, how hard can that really be, right? Well, the short answer is, on Earth, it's actually pretty easy. Really, most thermal control on Earth can be summed up in 2 things. If it's too hot, put a fan on it. If it's too cold, burn something. It's pretty much it, right? So, fans are wonderful. Look around you and you'll see fans all over the place, right? In your computer, on your car, right? Big power plants, all kinds of fans all over the place for cooling things off. But they don't really work too well in space, right? Because in space, nobody can hear you scream. There's no air in space. And also, burning things doesn't really work too well either. So basically, the things that we're kind of used to on Earth don't really work that well, and that's kind of a problem. So that has some interesting implications, and we'll kind of come back to that in a second. But really, whenever we talk about kind of thermal and heat and all this kind of stuff, what is that, right? So really, at the end of the day, temperature is a measurement of thermal energy. It's just a form of energy. And so really, actually, in many ways, a better name for the thermal system would be the energy management system. It's not really, thermal energy is just one form of energy. There's obviously other ones like electrical and chemical. But if you may remember from Thermodynamics 101, the second law of thermodynamics basically says that all of those other energy forms, whenever they're transformed, some of that ends up as heat. And at the end of the day, all of the other energy forms on the spacecraft, whether they're electrical from the solar panels, they're going to end up as heat. And so it kind of, everything becomes our problem at the end of the day. Just to give you some idea, here's a little diagram of a typical spacecraft, very high fidelity drawing here, a little box. And all of these different arrows are different sources of energy that basically can strike the vehicle. So, basically, obviously, whenever you're in the sun, you have some amount of energy coming in from the sun. If you're near a planet, particularly, a lot of CubeSats operate close to the Earth, you have albedo, which is essentially reflected solar, and then you also have planet shine. So the Earth is a warm body, and so it's actually emitting radiation, and so you have kind of the combination of those 2 things. So you usually don't get any albedo on the shadow side of the Earth whenever you're kind of, it's nighttime locally, but you'll still get energy basically being radiated. And then anything on board the vehicle, computers and so forth, will also generate energy on board. And then all of those ultimately have to leave via radiation because we don't, obviously there's no air in space. And so basically at the end of the day, the job of thermal engineers is kind of to balance all of these very quickly changing different inputs. You may turn on a computer and turn it back off, and that may make a difference of 20 watts or 50 watts or 100 watts. You may come in and out of the sun, which could make a huge difference. And so really, this is kind of us, right? This is an accurate picture of us working on trying to balance all of these brooms upside down and make sure that they all kind of balance out. But really, kind of from physics, this is the most math that I wanted to put in the presentation here, is basically just the rate form of the energy balance equation basically says that whenever you have an imbalance of these things, that your temperature is changing. And so, a lot of these things are outside of our control, and we have maybe a few knobs that we can turn, but really it's our job to make sure that the temperature changes as little as possible so we can keep it in that kind of Goldilocks range. So how does this actually work in practice? So a lot of the times, in most situations when dealing with spacecraft especially, heat is rarely distributed how we would like it. And obviously, physics says that there's no way to create or destroy thermal energy. So the best that we can do is either transform it or move it. And so really, if you kind of boil it down, again, all thermal control systems, no matter how complicated they are, have to really do kind of these three things. So heat acquisition is basically picking up energy from a place where you don't want it, something that is, in this case, basically too hot. Moving it to a different place with heat transport. And then using heat rejection to get rid of that energy, to deliver it to a place where it's not needed. So I'm using this example of a car engine because it makes for a good example, where you basically have acquisition. There's some coolant that flows around the engine cylinders. And then our transport here is basically the coolant lines. And then our heat rejection is the radiator. I put radiator in quotes because it's not a true radiator. It's actually a convector, but that's down in the details. Again, kind of thermal engineering jargon here. Another thing that you'll commonly see is thermal control devices typically get broken down into sort of active and passive. Active devices usually have kind of moving parts, like in this case, you have a fan, you have a pump that's circulating liquid. These are usually sort of bigger vehicles like the ISS, Mars rover, that kind of scale. Passive devices are simple things that usually don't have moving parts and don't require additional power. And so this is kind of the realm of where CubeSats sort of operate. So this was my attempt a while back. Somebody kind of asked me to try to distill all of my thoughts into kind of like a key takeaways. Obviously there's a lot of kind of details behind here, and we can kind of go into more details if you guys happen to have any questions. But trying to kind of get down some thoughts on a single slide of, if you don't remember anything as far as thermal control, try to remember some of these things or all of them. I kind of mentioned that thermal control is easy on Earth compared to space. So this is an approach of, oh, everything's going to be fine. It usually doesn't work that well when it comes to space vehicles. So we kind of have to sweat, so to speak, the details here. So in a lot of cases, the intuition that you develop from kind of being on Earth in kind of nice environments, it might lead you to draw wrong conclusions about something behaving in space. So and it's to a large degree. Typically things aren't just worse than you expect, they're significantly worse. Not to be alarmist or anything like that, it's just kind of the way that the physics sort of works out. And unfortunately, it's just really challenging to design like, oh, what's the best thermal system? Because it depends on so many different factors. So thermal systems are usually custom designed for the specific mission. And so, if anything changes between that, it may have implications for the design. So long story short there, don't just copy somebody else's design because there may be something drastically different that pushed them in a design different from yours, and using their approach may lead you in the wrong direction for your particular mission. There's also no free lunch when it comes to thermal control. The best we can do is come to different trade-offs. So, for example, you can't make something cool unless you make something else hot at the same time, right? Yes, I can try to improve the cooling, but it's going to be, at the expense of mass, or volume or both or something like that. So there's no, I don't have any kind of Goldilocks approach of being able to just magically do stuff. I need resources when it comes to doing this. The details matter a lot. So, you'll see situations where, the orbit may change by what seems like a small amount, but that actually may have profound implications as far as the thermal design. So, ignore those designs at your peril, basically. The other thing is actually that when it comes to modeling the thermal behavior of spacecraft, it's pretty complicated. We need to do orbital analysis, we need to do geometric modeling to make sure that we calculate view factors and so forth. And so in a lot of cases, a spreadsheet model may not give you an adequate level of fidelity to capture your behavior. So all of these things are things that we deal with on a daily basis. So come talk to your friendly neighborhood thermal engineer. We do this stuff day in and day out. We're trained to spot the details, and we are here to help you. So don't bite most of the time at least.
Thank you very much, Chris, for very fundamental and explanation of problems. And now we are turning to Mackenzie. He will talk about fundamentals of spacecraft design. Yeah, on.
I think you need to stop sharing your screen so that I can share mine. Wonderful. Give me 1 second. Here we go. Can you guys see that okay?
Yes.
Wonderful. So it's kind of a motivating example. I'm going to talk a little bit about physics of failure. I'm just a poor thermal engineer. I don't really understand what's going on down at the atom level, but I'll do a little bit of explanation just so we kind of know what's bad when things get hot. So generally in an electrical system, higher temperature leads to higher electrical resistance. And since the heat generated by a resistor scales with the resistance, that can kind of lead to a bad feedback loop. So that's one reason why electrical stuff breaks when you get it too hot. A different reason is less from getting something too hot, like at a single moment in time, but more about the amount of time that something spends at high temperature. This is a failure mode called electromigration. So somewhere on an integrated circuit inside your computer chip, there is some tiny little strip of conductor that is passing electrons through it. And if the temperature is too high, then those moving electrons cause the conductor atoms to just move away a little bit. And then all of a sudden you don't have a wire anymore, you have no wire at all. So this is worse with higher temperature from the Arrhenius equation. It's worse with higher current, and it's worse with really thin conductors, like the super small process integrated circuits. So this is all to say, if you are letting something run too hot, you are reducing its reliability and taking some time to think about the heat paths from your chip to the outside environment can provide great dividends in reliability here. Second. So one other one is thermal cycle fatigue. So this is, let's see, this is most famous on Earth for having caused the infamous Xbox red rings of death failure mode, if any of you remember that. So if you have a large enough chip with little solder balls connecting the chip to the circuit board, the chip and the board have different coefficients of thermal expansion. So as the chip heats up, or as the chip board system heats up, they expand different amounts, and so that puts strain on the solder balls, which in their frozen state are super brittle. And so if you expand and contract, expand, contract, expand, contract by a number of power cycles, or say starting your game, stopping your game, starting your game, stopping your game, then eventually some of these solder balls can break. And they're not just putting those things on there for fun. Every one of them is kind of an important electrical connection. This matters a lot in space because the thermal cycles that you see in space are huge. They're enormous. These are every 90 minutes you're doing some wild swing. Maybe I've seen a 90C swing before in an orbit if you've got really low thermal mass to surface area ratio. These are, let's see, this is a reason why thinking about the amount of thermal cycling that your chips are doing might be important. And let's see, this mostly depends on the amplitude of the swing, but it also somewhat depends on how high the top end of the swing is as well. So sort of two motivating examples here. planning better connections between your hot chips and the external environment is important here. And some of that can be just geometric. If you have a hot chip, place it close to the radiator. It is ideal, if you have a particularly high dissipation chip, minimizing the number of interfaces, of like surface-to-surface interfaces that the heat needs to get to before it reaches the radiator can be super helpful. One way, like Chris said, that our terrestrial experience kind of ruins us for thinking about thermal in space is assuming that two surfaces that are in contact are going to transfer heat across them. So I'm going to give a quick comic piece of advertisement here that I found from a thermal interface material company. Every flat surface that you see is actually kind of a little jagged surface, and when they are next to each other, they're only touching on those little jagged bumps. On Earth, there's air in between those jagged bumps, and so some of that interface resistance is smoothed out. However, in space, those little gaps are filled with vacuum, and so two flat surfaces that are nominally in contact barely make thermal contact in space, unless the pressure is super high and the area is super small. So you can see, for example, standoffs working okay as thermal paths, like a standoff between two circuit boards, just because of the relatively high pressure on the standoff base. This is a non-comic version of that lesson there. Yeah, I've got another slide, and that'll be for later.
So this finish presentation?
Yeah.
Okay. Thank you very much for very interesting thoughts. Now we are going to talk about importance of fundamentals heat transfer to validate the thermal model. Thomas, you're on.
Oh. All right. As I mentioned, I'm not a thermal engineer, but we are a user of the thermal engineering a lot because our hardware, basically in propulsion, chemical propulsion, you can't get too cold, as Elwood knows. You can get cold and your propellant can freeze, and it's very scary. On the other hand, you generate lots of heat when you fire thrusters, and they are very close together in the CubeSat. On our power subsystem, for example, not quite CubeSat, it's a half ESPA. We generate 5 kilowatt peak power for short duration, but it's definitely something we spend lots of time worrying about it. I have kind of 3 observations. One is the fundamentals matter. I guess it's my pet peeve is often that we got into this habit of computer modeling, and we all know the famous adage of garbage in, garbage out. It's always important to verify with the common sense. Some areas of engineering are hard to verify, validate intuitively, high energy particles or orbital mechanics. But in the thermal, ultimately it's a conduction. If I see a 200-degree gradient across a piece of aluminum bracket, it's probably not the right answer. There's something wrong there. Same thing with the, thermal inertia. People should intuitively know if I start dissipating heat in an object of this size, how quickly, is it takes seconds or hours to equilibrate to a new temperature. So if I can do something about the colleges, to systems engineering and space CubeSat, kind of aerospace department to emphasize, always kind of validate your computer model by does it make sense, either purely a hand calc or a simple model. The other one I want to emphasize is that we need a broader selection of, and I forgot to say, affordable thermal dimension devices. Ultimately, we can generate more power, solar panel get more efficient. We need more power, as Elwood said, and we can manage it, but we need a plethora, we need a supply, industry to supply affordable, basically we have heat pipes, but those are actually less important for a small spacecraft. We need thermal switches, variable coating surfaces, things like micro louvers, heat sinks with the phase change materials. There is dozens, hundreds of papers published about these devices, in the AIAA or NTRS or SCIE archives, but we need more companies to make these things at affordable cost. To me, that's always a perfect project for often a university CubeSat program. Sometimes I feel that these CubeSat teams often strive for very high requirements, imaging mission, which is difficult to do, but qualifying a new thermal switch or heat sink device on a CubeSat is a perfect example. It's a very high value mission, which I think is practically achievable. So I want to, again, emphasize to any student groups trying to think about building an next CubeSat, this is definitely an area where I think would be very high utility in demonstrating, and ultimately there is a market. I think there is a need for these devices. And my third point, which is kind of personal peeve, we made a huge improvements in user friendliness of all kinds of system engineering tools, from orbital mechanics, mission design, software development, structural analysis, requirements tracking. If you look what we have access today compared to when I started my career in 90s, this all improved. For some reason, thermal, not point to any specific company here, but thermal FEA tools are still stuck in their mid-90s design. And it is a problem because it creates a very stovepipe discipline, because it takes a long time to learn the tool. Not only you have to learn the engineering, but you have to also learn the tools. And I think that's an area where we should see some improvement over the next couple of years. I don't know who will do it, but I think there is a need for that.
Yeah, thank you very much, Thomas. So this is it's logical right now. Ask John to get into picture, because John is working for a company which actually does a lot of stuff for big satellites, and now hopefully that we will get this something, as you, Thomas, said, we need to have for CubeSats, small satellites. Yes. So, John, can you just tell what's going on?
I'll attempt to. Again, my name is John Thayer. I work with the Boyd Corporation. Been making heat pipes for 25 years. I want to discuss several of the passive heat transport elements that have been mentioned already: axial grooved heat pipes, copper water heat pipes, loop heat pipes, and then thermal straps and embedded graphite structures. Radiators, of course, are part of the picture, but that's not what I'm going to talk about. I'm mostly talking about these other elements that transport the heat from the heat source to the radiator. I will also touch a little bit on additive manufacturing and integration with CubeSat structures. This diagram shows an array of the different heat transport elements that can be used. Axial grooved heat pipes, they are the standard heat transport mechanism in satellites. They are sometimes called constant conductance heat pipes. They are aluminum extrusions that have grooves on the inside. Those grooves serve as a capillary structure that transports the condensate and the heat pipe back from the condenser to the evaporator. In addition to axial grooved heat pipes, there are copper water heat pipes that have a sintered copper powder structure, or sometimes a wire screen structure, wick structure. Loop heat pipes are a more complicated design element and with more capabilities. Let's sort through some of these things. So you can see here in the overall picture, the axial grooved heat pipes are part of the radiator structure. In the bottom, copper water heat pipes often go attached directly to electronic components and transport heat over to the cold rail, or sometimes they're embedded in the sides of the chassis to improve the conductance of the chassis. Loop heat pipes typically gather up heat from all the sources and take it out to a radiator. The radiator is not shown here, but in addition, there are thermal straps and embedded graphite that serve as point cooling mechanisms for particular heat sources. Here now, axial grooved heat pipes. You can see what the internal structure of the grooved is. More grooves means better heat transport, so a larger extrusion can accommodate higher heat loads. Ammonia is the usual working fluid. It's good from approximately plus 50 C down to minus 50 C. If you need to go below minus 90 C where ammonia freezes, propylene is the usual choice. Often axial grooved heat pipes are embedded in the honeycomb radiator panels. Sometimes they are formed into bent to shape solutions that transport heat from a heat source to a radiator. They're usually in the 0.5 meter to 3 meters in length range and usually transport from 10 watts to 250 watts. You can imagine looking at the profile of an axial grooved heat pipe that it could easily be integrated into a CubeSat structure. One thing to be pointed out about axial grooved heat pipes, they do not work against gravity, and that complicates the life of spacecraft thermal engineers who are trying to test their satellites before they launch them. Copper water heat pipes are the most common form of heat pipes. Virtually everybody's laptop computer has some copper water heat pipes inside. They're easily bent to shape. They are often embedded in aluminum structures. Shown here is a chassis wall with copper water heat pipes embedded in it. Often people are concerned about water freezing at below 0 C. Copper water heat pipes are typically freeze-thaw tolerant, and they've been tested to thousands of freeze-thaw cycles. A usual part of the acceptance test is 25 to 50 freeze-thaw cycles. Typical lengths are 10 centimeters to 30 centimeters. Typical heat loads are 10 watts to 30 watts. Just to say an aside here, heat pipes are usually thought in terms of as pipes, as tubes. There is the same heat transfer physics available in a three-dimensional structure, usually called a vapor chamber. So some heat loads in space are getting to be high enough that they warrant vapor chambers, not just heat pipes. A loop heat pipe is a more complicated heat transfer structure. It has a distinct evaporator and a condenser with not one, but two tubes in between, one tube for the vapor, the other for the returning liquid. The evaporator and condenser can be meters apart. And these transport lines can be flexible, so they can be used as deployable radiators or thermal transport mechanisms for moving devices. Typical heat loads are 100 watts to 1,000 watts. You can get the sense that these are specialized, i.e. expensive devices. We do make a mini loop heat pipe with a 5 centimeter evaporator. So we do make a loop heat pipe that would fit into the CubeSat size range, although it's probably more than what most CubeSats really need. Thermal straps are another choice. These are pretty straightforward. They're stacks of conductive foil. You can see in the photos that they have quite a bit of geometric flexibility. You can create lots of different shapes. You can add more straps to get more conductance. Copper, aluminum, and graphite are all choices. So those are, again, these are typically point solutions. Embedded graphite is another choice. In most embedded graphites applications, annealed pyrolytic graphite is put together with an aluminum structure in sort of a jigsaw puzzle kind of way. Then the aluminum is all sealed up and hipped so that it's ultra compressed. And then it's machined to shape. All the extra aluminum is cut away, and you're left with a shape that's just exactly what you want. These are purely conductive solutions. They're easily integrated, you can imagine, into a CubeSat structure. This is just another piece of aluminum. Again, these are specialized, but not quite as expensive as loop heat pipes. It should be pointed out that graphite has really high thermal conductivity in the X and Y directions, over 1,000 watts per meter K as compared to copper's 380 or aluminum's 200 watts per meter K. Unfortunately, you can't get everything. In the Z direction, the thermal conductivity is less than 10 watts per meter K. So you have to design that into your application.
I'm sorry, John. Thank you very much for your, we are running out of time a little bit. So if we have time, we come back to your presentation.
Okay.
Okay. So now we come into the most exciting part of our panel, namely your questions. So do you have questions? Yes. Mm-hmm. So who wants to answer?
Did you guys hear the question?
Do you mind repeating the question? Do you mind repeating the question for those of us on remote?
Yeah, let me see if I can summarize it. So the question is basically about the trade-off between delta T and max temperature. So would there be situations where you would potentially accept a higher max temperature in order to minimize the delta T? Did I get it? Yes. Okay.
And is that in a thermal cycling regime, or?
Say again. Say again, Mackenzie.
Is that like in terms of thermal cycling for fatigue purposes, or like delta T between hot chip and cold radiator?
Both, yes.
Okay. For thermal cycling, it is definitely preferable to have higher temperature than it is to have wider temperature swings. The amplitude of the swing is a much bigger factor than the I don't know, height. So if you have to trade directly between the two, then yeah, I'd pick higher temperature. However, higher temperature opens you up to a whole bunch of other failure modes, and so be careful that you don't go too high. Or if you're going to go too high, be sure that you have tested exhaustively whether or not those components can go that high. You can get yourself out of some tight holes with a good testing regime.
Is answered your question?
Yeah, I mean, of course, there's some practical upper limit as to how hot you can get anything, right? I mean, you're not going to be able to take a component, 50 degrees beyond its kind of rated limit. But yeah, in general, it's definitely difficult to deal with the widespread. So yeah, I mean, it's, minimizing the delta T is always beneficial, because you can run into situations where it's like, I have simultaneously something that's too cold and something else that's too hot, right? It's like that type of situation is just kind of difficult to do. So. The question is, follow on, is there an advantage to adding a heater? Yeah, in general. So it all depends on what resources you have available, right? So you can obviously, convert electrical energy into heat pretty easily. That's easy to do, but it requires that you have that power available to do that. So if you're in a situation where the mission is power starved, so for example, the one mission that I've worked on was Europa Clipper. It's solar powered out at Jupiter, and the available sunlight is about 1/50th of the heat flux that you get on Earth. And so every watt on that thing is extremely precious. And so it basically kind of drives the design away from, I don't have abundance of heaters to just be able to burn electricity everywhere on the spacecraft, right? I have to harvest the heat, the waste heat from computers, move it somewhere else to keep things warm. So, it all really, the design comes down to what resources you have available. So, and in some situations, the design just may not have electrical power to be able to convert into heat. So in an ideal world, I mean, if we had our way, right, we just put heaters on everything and a big radiator, just call it done. But we have to work within the rest of the constraints of the mission. So.
Well, you also have to look at the spatial gradients because heater won't be at the same place as the, let's say, solar input. So even though you may be maintaining average temperature same, you are driving gradient, from one side of the box to the other side of the box back and forth. That's obviously, spatial gradients are as bad as the temporal gradients in temperature or cycles.
A number of these heat pipes can be configured as thermal switches that will reduce conductance in cold conditions. The simplest would be a copper water heat pipe. When the water freezes, it stops conveying heat effectively, and so will limit heat loss in cold conditions. Loop heat pipes have an option where you can use a PID controller to control the temperature of the reservoir and apply a couple of watts to the reservoir. You can turn off the loop heat pipe and cease circulation. So those are a couple ways of managing limiting heat loss in very cold situations.
So does somebody want to add to the discussion? Okay, so other questions, guys? Yes.
So for the people online, there's a team doing a 1U CubeSat. They're having a challenge in modeling their thermal behavior. And so the question is, are there tools? What tools can they use?
To do this simulation, I believe that, Thomas, you have some suggestions.
I mean, I will let you discuss the tools, but I also would say start with the simplest model. One thing about CubeSats, especially 1U CubeSats, I mean, it's going to be no difficult to design as far as isothermal. You aren't going to have a 50-degree gradient across 10 centimeters unless you are doing something really difficult or crazy. And obviously, the nice thing about the cube is a pretty constant cross-section. It's tumbling in Earth orbit, so for example, the thermal radiation from the Earth is going to be pretty well constant. Solar input, unless, again, you add deployable panels, but if you have a body-mounted panels, you can average, I think, you definitely should do a sanity check first to make sure we have a right amount of power in and out. And I'm sure there are simulation tools that can recommend in more detailed analysis.
So yeah, to answer your question, so there's basically two kind of main thermal analysis tools that I'm aware of. The first is called Thermal Desktop. It's by a company that's called CNR Tech that was just recently bought by ANSYS. It's essentially like a plug-in for AutoCAD, and it will do all of the radiation view factors for you. You can put in an orbit, and it'll calculate all of the heat loads as your spacecraft goes around. So that's commonly used. And then the other one is called Space Systems Thermal, which is kind of a plug-in for NX by Siemens that's also used as well. I haven't used that one personally. I've mostly been using Thermal Desktop, but those two are kind of the core of the space thermal analysis providers.
My suggestion, don't use Thermal Desktop.
I was about to say exactly the same thing. Don't use Thermal Desktop for your 1U CubeSat. It's way harder than the information you'll get out of it.
And the reason because Thermal Desktop is actually very versatile, but it's evolved. You know, this you will sink, so you cannot, particularly if you started this, don't use it. It takes like 5 years of thermal engineering in order to master Thermal Desktop.
The learning curve is pretty steep, that's true. Huh? The learning curve is pretty steep.
Yeah, so
don't. I would recommend just doing a hand calc.
Yeah.
Just how much heat is coming in from the sun, how much heat is leaving via radiation, how much heat am I generating on board the spacecraft via running my computer or what have you, and just make sure those numbers are near each other.
I mean, that's the beauty of 1U CubeSat. it's going
Yeah,
to be
exactly. Yeah, like you said, Tomas, you're not going to get a 50C gradient across your 10-centimeter cube.
Yeah, not to mention that it used to be $7,000 license fee. Now I guess it will be much more when CRTech lost independence. So, okay. So, other questions? Yes. As far as I know, louvers for CubeSats was built by one of the NASA centers, right?
I will tell you, we would love to buy them. If there is a company selling them for a small scale, we'll buy them. We will get a purchase order right away. But so somebody needs to build it.
Yeah, I think it was built by one of the NASA centers. This what.
Yeah, so it's not for sale, you can license it.
No, unless you pay in NASA budget. This is probably, who wants to answer this?
Mass and size.
Yeah. I mean, it's not like building a fusion reactor. It's a straightforward engineering, but it does take, I don't know, hundreds, a couple thousand hours to really validate, qualify, understand lifetime. And I think that, unfortunately, the issue is the market, at least from my perspective as a small business, is that it's a market size, and, for a large spacecraft, you can charge 100,000, tens of thousands, hundreds of thousands of dollars per device. On a CubeSat market, you can probably charge a couple thousand per device, and it's hard to make a company work around selling $4,000 devices because you just don't sell that many of them. So that's the bottleneck, I think, that we need more CubeSats using them, or we need, I don't know, somebody figure out some clever way to make them for $400.
Yeah. And the other problem with that is looking at just the form factor and trying to keep anything attached to the outside to be compliant with the standard, right? That you have to make sure that you're going to be between the rails, and stuff like that. And deployables, a lot of CubeSats have them, but a lot of people are just at that point that it's so much easier if you don't have deployables for CubeSats. Especially for university type of missions.
But if you do, it's a fun project.
It is. It is.
Other questions, guys? We have about a couple minutes left, but if you want to stay, we're going to stay as well. So, other questions? Yes. Mm-hmm.
So the question is about a commercial off-the-shelf component that's cryo-cooled and has not been TVAC tested by the vendor. So basically, just like, what are things we need to look out for, and are there any kind of red flags from that?
As far as I know, there is a couple cryogenic-based CubeSats built by, I don't know, is it flown by Navy or not?
Lockheed Martin did one.
It did.
The micro-cryo cooler.
May you just explain? Okay.
And I don't know how successful. I have not actually seen it being transferred in the market. I think some folks in SMD actually used it on a couple of their missions, but I don't know how effective it was. But I have not seen a lot of commercial and other demands. I think they've most spacecraft look at other means of handling thermal control. I think the Utah State, for example, had the deployable baffle with a liquid in it to help the thermal cooling. So there's other ways to look at that. I think one of the things with the micro cryo coolers that, at least the early ones that I was involved with, they required power to operate. And so now you're starting to trade cooling with actually adding more power into the system and raising your power requirement.
As far as I remember, it was no, I was involved in cryo CubeSat, and so in order to remove 1 watt, it takes 25 watts.
Yeah.
So this is one, and another about the commercial. As far as I know, again, I wasn't involved. Just talking to engineers from Lockheed Martin. As I said, don't buy anything commercial. And the reason because vibration will kill you. So.
Yeah, if the vendor did not teabag the unit, you should. Or you should teabag the whole spacecraft once you got the unit integrated into it. Like there's so many ways you can kind of get this wrong, and most of them will be some kind of thermal interface resistance. So when you do your teabag test, make sure you have some kind of thermocouple or thermal sensor, basically on every element in the heat path, to figure out if one is not performing like you'd expect it to.
Yeah, I want to emphasize this is a system. It's not just buying a micro cooler, but you have to design a radiating surfaces. Right. You have to design actually I assume some kind of sensor, doer or some kind of, you have to isolate. You have to worry about how to actually attach wiring to the cryogenically cooled part, because you can easily kill all the heat, and there's a control system. So it's not just getting the device. It's a fairly complicated system design, systems engineering process.
But again, of course, if you want to save money, you can buy commercial, but then you are known, or probably you need to spend more money buying from Lockheed Martin. So this is a choice, essentially. Yeah, more questions? Actually, I am not familiar with presentation. Somebody.
So, John, in your presentation, there was an image where you had a honeycomb panel with a heat pipe in it, and the question is there a thermal reason why we use honeycomb?
Okay.
No. The heat pipe thermally connects to face sheets on one or both sides. The honeycomb is merely structural reinforcement, lightweight structural reinforcement.
The honeycomb is actually is not a great thermal device at all, and that's why you got heat pipes in it. What honeycomb maximizes is rigidity per unit mass, and so the structural engineers like it, and the mass budget folks do. But then you got to stick heat pipes in it in order to make heat spread. So trade-off.
For example, one area where it's not a really thermal but structural is that we are used to honeycomb panels on large spacecraft. It's a very common approach. But you notice that in CubeSats or even small satellites, kind of ESPA class and sub, honeycombs really don't often pay off, because by the time you get in theory, it's a very efficient structure, but by the time you get all the edge trimming and inserts and get a real hardware, often a machine structure becomes as effective as the honeycomb. So there's definitely a culture change from a large spacecraft to a small spacecraft, that things which work very well in a large mission don't kind of break down in a small scale.
Other questions?
I don't think I would use honeycomb for anything smaller than half a meter.
Okay, yeah. That sounds about right. Yeah, I would argue that half a meter by the minimum size pay off.
So other questions? No questions. Okay, so then I guess, John, it concludes our presentation and our panel.
Thank you very much. Cool. Thank you, Boris, and thank you, everybody. I appreciate everybody coming here. I hope you enjoy the rest of the day. If you're here this evening, I do encourage you to check out Farmers and be on the lookout for all of the information that we'll get out about the workshop next year. And again, thank you and have a great day. Thank you very much. I appreciate it. Okay. Other than the first